These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. Let me introduce a new notation that you and I haven't used yet. So how do we read this aloud?
The derivative of y over the derivative of x, I guess?
Not quite. So let's talk about that.
Okay.
This is read as, have you seen this notation in class?
Yep, I have.
But it's a confusing notation. This is the derivative of y with respect to x. The derivative of y with respect to x.
Okay.
So notice d does not stand for derivative. This is not derivative of y divided by derivative of x. It's the whole thing together that stands for derivative. You can't just pick out the d and say it's a derivative. It's not one derivative over another. It's the derivative of y with respect to x. Okay? So how would you read this aloud?
That's a, so I guess it's the same thing. So the derivative of f with respect to x.
That's right.
So it's always, okay.
So how would you read this aloud?
Okay, it's the same thing. So it's the derivative of g with respect to y.
Okay, that's right. Okay. So how would we read this aloud?
The derivative of y with respect to x equals 3.
Good. Now how would we interpret that? What does that mean? And this is something that you and I have actually worked on. We haven't worked on it with this exact notation, but we've done quite a bit of practice on interpreting what does this number 3 tell us?
So as x increases by 1, the value of the function increases by approximately 3.
By approximately. Good. Right. What's the value of what function?
Of y with respect to x.
Okay, close. We can just say y. So
y.
This tells us that if we increase x by 1 unit, y will increase by approximately 3.
Okay.
If we increase x by 1 unit, y will increase by approximately 3. So how would you read this aloud?
The derivative of y with respect to x is 5.
Good. And how would you interpret that?
As x increases by 1 unit, the value of the function y increases by approximately 5.
Excellent. Great. Or you could just say as x increases by 1 unit, y increases by approximately 5. Good.
Okay. The derivative of g with respect to z is 6.
Good. And what does that mean?
As z increases by 1, the value of the function g increases by approximately 6.
Excellent.
The derivative of f with respect to x is 7. And that means that as x increases by 1 unit, the value of the function f increases by approximately 7.
Excellent.
The derivative of f with respect to y is 2. And that means as y increases by 1 unit, the value of the function f increases by approximately 2.
Okay, very good. Now, let's compare these two statements. How are they different? So one thing that I think a lot of students don't understand is, why do we need this business about with respect to? We never talked about this with respect to before. What is that adding? Well, you can tell that by comparing these two. How are these different? So this tells us how much the function changes when we change x. If you change x by 1 unit, the function will change by 7.
Okay.
But this tells us how much the function changes when we change y by 1 unit. So hopefully that makes it clearer why we really have to say what we're taking the derivative with respect to. What's the whole point of derivatives? The whole point of a derivative is it's a way to figure out how much the function is going to change. The derivative tells you how much the function is going to change when you change the input. But there are different ways to describe the inputs. There are different inputs you could change. So if you're changing the x input by 1 unit, this function will change by 7. But if we're changing the y input by 1 unit, the function will change by 2. Now, these could be the same exact function. These could very well be the same function f. It's just that we're changing 2 different inputs. Here we're changing the x input by 1 unit, and here we're changing the y input by 1 unit, and that gives you totally different results. So hopefully now we can understand why the bottom here is necessary. And what this with respect to means a little bit more clearly. Okay, so notice that this D here doesn't stand for derivative, even though it looks like it. It stands for with respect to, right? So it's not very logical. But technically, this D doesn't stand. So actually, this D kind of does stand for derivative, right? Because we really are taking the derivative of f. This D really does stand for derivative. But this D doesn't really stand for derivative. It stands for something you would never expect. It stands for the phrase with respect to.
Okay.
By the way, notice that this is written as a fraction, but right now we're not really interpreting it as a fraction. So you should not split this up into 2 different pieces. This is not d of f divided by d of x. We're just treating it as one big glob of a symbol. So right now this is not really a fraction, even though it looks like one. There is a way, it actually is possible to interpret this as a fraction, but that's a little bit of an advanced technique that your course hasn't reached yet. So right now the point is we're not giving d of f, we're not giving df a separate meaning, and we're not giving dx a separate meaning. They only mean something right now when we put them together. And when you put them together, this means the derivative of f with respect to x. Okay. Now, all of the functions that we did before, we never talked about who we were taking the derivative with respect to, right? Mm-hmm. Well, that's just because we always did it with respect to x. Since we were doing it with respect to x every single time, it would have been boring to say that every time. So if you're usually in calculus, you usually take the derivative with respect to x. And since you're doing that, you don't have to say that every time. But if there's another variable that you could be taking the derivative with respect to, you have to be more careful. So what does this symbol mean?
That's derivative of y.
Good. But now this is the symbol we've used in the past, right? Mm-hmm. But now you can see that this symbol has one big shortcoming. The shortcoming is it doesn't tell you who we're taking the derivative with respect to.
Right.
So generally you just have to assume usually that you're taking the derivative with respect to x when you're using this symbol, or that you're taking the derivative with respect to a variable that's natural, that you already know. So the advantage of the prime symbol is that it's simpler. The disadvantage is that you have to assume who you're taking the derivative with respect to. The disadvantage of this symbol is that it's a little more complicated, but the advantage is that it tells you who you're taking the derivative with respect to. All right. Also, I have to show you a couple other ways we can write this. So, for example, this, how would you read this aloud?
That's the derivative of f with respect to x.
Is the same exact thing as this. These have the same exact meaning.
Okay.
So these are just two different symbols that we have to get used to. So how would you read this aloud?
That's the derivative of f with respect to x.
So the point is, you don't have to write the function on top. You can also write it off to the side. One time that's oftentimes helpful is, for example, suppose that you're trying to do this. What does this mean?
That's the derivative of x squared plus 3x with respect to x.
Right, good, excellent.
X.
Now you could write that like this. Instead of naming the function, we could actually just write the function down. So my point is, when you actually write out the whole function, it's less common to try to fit it on top of the line and more common to kind of write it off to the side, like this.
Okay, that makes sense.
But these both mean the same thing. So notice there's two ways to do this. You could write the name of the function, or you could actually write the actual function. By the way, what is this? What is this derivative?
That's 2x plus 3.
That's right. So in the past, we would have written that like this. The way we've learned how to write that is this. Here's the notation we were using for that before. The only downside of this notation is that it doesn't say what we're taking the derivative with respect to. However, the most natural assumption here is that we're taking the derivative with respect to x. So that's what we've been assuming when we used a prime in the past here. So what's this?
That's the derivative of x to the n with respect to x.
Now that last part was just a guess, but that's a reasonable guess. You can't tell for sure what we're taking the derivative with respect to here, but in the past we've assumed it was x. That's right. But so actually, what is that derivative?
Okay. X to the n would be nx to the n minus 1.
That's right. This is what we call the power rule. Now remember, the power rule only works when, is this a variable or a constant?
The power rule only works when the base is a variable and the exponent is a constant.
That's right. Good. Now here's a different way to write the power rule. What would this be?
It's the same thing, so it would be nx. Yep.
This is a slightly superior notation because it confirms we're taking the derivative with respect to x. This tells us how much this function changes when we change x by 1 unit. Now, what's this? Well, the thing I have to tell you is we don't have any idea what this is. The power rule, so this is the power rule. The power rule says that when you're taking the derivative of x to the n with respect to x, then you can take the exponent down and reduce it by 1. The power rule doesn't tell you anything about the derivative of x to the n with respect to y. I think we've seen in the past that you have to be careful not to apply these simple rules where they don't apply. And here's another example. The power rule doesn't apply unless you're taking the derivative with respect to the base. It only applies when you're taking the derivative with respect to the same variable that's in the base. If you're taking the derivative with respect to a variable that's not in the base, then we have no idea so far what this derivative is going to be. So all along, when we were doing these derivatives, we really were assuming that we were taking the derivative with respect to x. But if there's more than one thing that you could be changing, you have to be more specific and write it in these two different forms. So we have to be careful not to apply the power rule where it doesn't apply. It doesn't apply in this case. Okay, good. Now remember, what's the difference between these two things? Well, remember, this derivative tells us how x to the n changes when we increase x by 1 unit. But what would this derivative tell us if we knew it?
Right, so this one is with respect to y, so it's when y increases by 1 unit.
It tells us
the value of the function.
Not the value of the function, but how much it would change.
Right. Okay.
So this would tell us if we increased y by 1 unit, how approximately how much the function would change. This tells us when we increase x by 1 unit, approximately how much the function would change. Well, those are two completely different things. These are two different inputs, so there's no reason to assume the function would change the same in both cases. Okay. Evaluate this.
1.
That's right. Good. But what does this really mean? What are we assuming we're doing here? It really means this, right?
Mm-hmm.
You're assuming you're taking the derivative with respect to x. So what is dx over dx?
1.
By the way, remember I told you that this is not a real fraction, but you can see why the mathematicians like writing it as a fraction, because if it were a fraction, it would cancel to 1. Although you shouldn't actually cancel these. We're not really treating it like a fraction yet. But of course, anything over itself is 1, so there's kind of a kind
Right.
well, I don't know quite how to phrase it. Okay, so we're not treating this as a fraction, but if we were treating it as a fraction, it would make sense that this was equal to 1. Now here's a trick question then. What's this?
Well, the derivative of x with respect to y. So 1.
Let me give you some help with that. So the point is we have no idea.
Okay.
This is the same as we were just doing for the power rule, right? The power rule only works when you're taking the derivative with respect to x. So if you're taking the derivative of a variable with respect to itself, the derivative is 1.
Okay.
But if you're taking the derivative of a variable with respect to some other variable, we have no idea what it is. By the way, how would you interpret this in words? What does this mean?
The derivative of x with respect to x is 1.
What's the interpretation of that?
Derivative. Okay, so as x increases by 1, the function increases by about 1.
Which function is that? Which function increases by 1?
I guess derivative. I'm not sure.
Well, you can't use the derivative to interpret the derivative. What would this mean?
The
How would you interpret that?
As x increases by 1, then the function f increases by about 5.
That's right. So who's increasing by 5? F.
F.
How would you interpret this?
Z would increase by about 7.
When x increases by 1.
Mm-hmm.
So how do you interpret this?
So as x increases by 1, then x also increases by about 1.
Right. In fact, we've seen that sometimes the approximations are exact, right? You know, if x increases by 1, how much would x increase by?
1.
Yeah. This is another case where we've talked about how when things are very simple, for some reason that makes it difficult for students.
Mm-hmm.
So the point here is, before you memorized that x prime was 1, but now you should understand why x prime is 1. Why is the derivative of a variable with respect to itself 1? Well, that just means that when you increase the variable by 1 unit, the variable increases by 1 unit. We've just kind of proven that this is the correct derivative here. Okay.
Well, I thought we proved it by the power rule.
Well, that's right. But we never really proved the power rule.
Okay.
Now we actually understand why this derivative makes sense. We've actually shown that the derivative of so you could prove this with the power rule, but we don't really understand why the power rule works. We just memorized it mechanically. But we should now understand why the derivative of a variable with respect to itself is 1. That just is repeating the obvious truth that if you increase the variable by 1 unit, the variable increases by 1 unit. It's not a very deep insight into the nature of the universe, but even trivial things are useful to understand in math. Okay, so but then you can see why we certainly can't assume that this is 1 then, right? Obviously, if you increase x by 1 unit, we know that x will increase by 1 unit. But does that mean that if you increase y by 1 unit, does that mean x has to increase by 1 unit?
No.
No, we have no idea what the relationship between these is. Okay. All right, so anyway, my point here is you have to be very careful about what you're taking the derivative with respect to. We haven't been thinking about that previously, but now we have to start being more careful about that. So what is this?
1.
What is this?
Unknown.
What is this?
1.
That's right. What is this?
That's unknown.
Good. So notice that we only know how to take this derivative of a variable with respect to itself. How would you interpret this? What does this tell us?
As z increases by 1 unit, z also increases by 1.
Yeah, we don't have to say also. If z increases by 1 unit, then z increases by 1 unit. That's not a very, again, deep insight, but it's true. Anything that's true is useful to write down in math. But does that mean that dz dw has to be 1? No.
Nope.
If we increase w by 1 unit, z doesn't necessarily have to increase by 1 unit. That would not be so obvious. All right, good. So what's this?
1.
Good. What's this?
It's unknown.
Good. What's this?
3. Maybe I have bad algebra. 2. Well, I guess, yeah, that's not really a fraction.
Maybe this would make more sense if I wrote it like this.
Okay, so as x increases by 1 unit.
Well, let's not. And now, at this point, we can't actually work it out anymore. So this is just a review. So how would you read this in words? What is this telling us to do?
The derivative of x cubed with respect to x. Okay, so just a normal. This would be 3x squared.
That's right.
Okay.
Why did that give you trouble? Because you're used to it being written differently, perhaps. We're just starting to get used to this notation here. All right, good.
Okay, this is 4x cubed.
You're using now the power rule.
Mm-hmm. That's because we're taking it with respect to x.
So what's this?
This is unknown.
Okay, good. You were already seeing where I was going with that. Can we apply the power rule here?
We cannot.
No, the power rule only applies when you're taking the derivative with respect to the same variable that's in the base. However, you can see that if we hadn't just been talking about that, it would be very tempting to write 4x cubed here. So that's one of the most common mistakes that people make that we now have to watch out for. We have to be careful about what we're taking the derivative with respect to. That's something we hadn't really thought about in the past. We can't apply the power rule unless we're taking the derivative with respect to the correct variable. What's this?
This is unknown.
Good, that's right. I was trying to trick you into doing 5z to the fourth, but you didn't do that. Good. And what's this?
5z to the fourth.
That's right. Okay, good. Okay, so now we can see why it really is important to say what we're taking the derivative with respect to. That's an issue that we've kind of been skirting over in the past. And now remember, what's the difference between taking the derivative with respect to q and the derivative with respect to z? What does this derivative tell us? What does this derivative tell us?
It tells us that we can... Maybe I'm not answering that question correctly. I was going to say it tells us we can use the power rule, but...
What I was going for here, it was kind of weird. This tells us, this derivative will tell us how much z to the fifth changes approximately if we increase z by 1 unit.
Okay.
It depends on where you are, so it's a little hard to interpret. But this tells us how much z to the fifth will change approximately if we increase z by 1 unit. But that's not what this would tell us. What would this tell us if we knew it?
This would tell us when q increases by 1, or yeah, when q moves by 1 unit, then we don't know how much the function of z is going to increase or decrease.
How much which function will increase or decrease?
Z.
Now actually z is not the function that we're taking the derivative of here.
The derivative of z with respect to q.
We're actually not taking the derivative of z with respect to q. What are we taking the derivative of? Might be a little difficult to get used to the notation. You're taking the derivative of z to the fifth.
Oh, okay. Okay.
After all, is the derivative of z to the fifth the same as the derivative of z?
It is not.
Now, what would this derivative be?
1.
That's one reason why we have to be so picky about knowing what we're taking the derivative of. There's a big difference between taking this derivative and this derivative. All right, so anyway, I just wanted to review the idea that it does make a difference what you're taking the derivative with respect to. Because the derivative is supposed to tell you how the output changes when we change the input by 1 unit. Well, this tells us how the output changes when we change input q by 1 unit. But this tells us how the output changes when we change input z by 1 unit. Okay, so hopefully now we're getting a somewhat better understanding of this d over d notation and this idea of taking the derivative with respect to another variable. And we're starting to see some having a better idea of what the derivative rules we learned about before are. We have to understand when we're allowed to use the rules and when we're not. We are only allowed to use those rules if we're taking the derivative with respect to the correct variable. We can only use the power rule, say, when we're taking the derivative with respect to the same variable as in the base. Okay, so what are we going for here? So what we're working on now is the material in the section on implicit differentiation. This is all material that you need to understand for implicit differentiation. In fact, I think we're ready now to start doing the implicit differentiation. So there's a bunch of, we have to do this preliminary work to understand what's going on in the implicit differentiation. And now we'd be ready to go on and to work out how to actually do that implicit differentiation. So when you do implicit differentiation, you're usually going to use this type of d over d notation. So we had to review what that means. All right, try this problem.
Okay. So derivative of y cubed with respect to x. So we can just use power rule, 3y squared. Okay.
Okay. And did you have a chance to review what we went over last time?
Mm-hmm.
Okay. I'll go back to my screen.
Okay.
Let's try this problem.
Okay. Well, Okay.
Oh, all right, good. I didn't quite write down what I meant, I guess. So I'll go back. Let me write down this problem. Let's try this.
Okay. Okay.
All right, you can erase that derivative of x cubed with respect to x. That was, I didn't mean to do that example. So how would you read that first line?
The derivative of y cubed with respect to x.
Good,
And then
that's right. Is
the
3y
next-
squared. And how would you read the second line?
Okay. The derivative of y cubed with respect to y is 3y squared.
So you're saying that both derivatives are exactly identical.
Right, which must be incorrect. So, well, I guess on the top example, I thought that as long as you're taking it with respect to x, that it's valid, but I guess it doesn't make sense if the variables are different.
That's true. Okay. So this is one of the topics we were talking about at the end of our last session. So
Right.
do you remember how did we handle this? What was our discussion there for that? So which of
Okay.
these derivatives do we need to change?
We need to change the top one.
Okay. So what would be the correct answer there?
It would be a question mark as of now. So,
Good. Let's just write it as unknown. So when you go back to your notes, you'll see that that's not the question. We just don't know it. Okay. So the thing that we discussed is that the power rule only works when the variable that you're taking the derivative with respect to is the same as the variable inside the function. It's a little hard to put it into words, but the power rule only works for examples like the one down below, not for examples like the one up above. Okay. So this is what we were talking about at the end of our last session. So it looks like you had misremembered that somewhat. I think you had misremembered it, and you remembered it as the power rule only works when you're taking the derivative with respect to x, or something
Right.
like that. But if that was true, then your second line wouldn't be right, because the second line was not with respect to x. So that was misremembering it. What made you think that? Well, what made you think that is that in the past, almost all of our derivatives have been with respect to x. In the past, we usually have taken derivatives with respect to x, so that made it seem like that was the key aspect. But the key aspect is not that the derivative has to be with respect to x. The key aspect is that the derivative on the bottom of the derivative we're taking, the variable we're taking the derivative with respect to has to match the variable in the function. Okay. So that was the key thing that we had to review there about that. All right, so I'll go back to my screen.
Okay.
Okay, so let's try this problem.
Okay. Derivative sine of y with respect to x. Oh, this is unknown. Okay.
Okay, good. All right, so I'll go back to my screen. So I was trying to trap you there. So the answer is unknown. What would a mistaken student say? A mistaken student might think that the derivative was cosine y. they might just try to apply the derivative, simple derivative rule we learned for trig functions before. But all of the simple rules that we've learned only work when this variable on top matches the variable on the bottom. So all of the rules that we've learned only work when these two variables match. So the rule that we've learned is this: the derivative of the sine of x with respect to, what variable should I write here?
X.
Yeah. Or you could write that simple rule like this: the derivative of the sine of y, but then what variable would go down here?
To y as well.
So remember how earlier you were saying that the key was that you have to take the derivative with respect to x, but that's not quite right. You can take, any variable can be on the bottom as long as it matches the variable on the top. The key is not whether it's x or y or z, the key is that these two variables have to match. So again, this is true for all of the simple rules that we've gone over. The derivative of logarithms, the derivative of exponential functions, the power rule, all of these things only work if you're taking, if the variable that on top matches the variable on the bottom. Okay. Good. So is there any way to simplify this?
Yep, we can just write 1.
Because the derivative of x with respect to x is 1. That's a rule that we've learned before. Is there any way to simplify this?
We cannot, it's unknown.
Yeah, this is unknown. You can't just say that this is 1y to the 0, which equals 1, because that would be using the power rule, and the power rule doesn't work when the variable on the top doesn't match the variable on the bottom. So this can't be simplified. I'll write that as can't be simplified yet. But this certainly could be simplified. How would you read this symbol aloud?
It's the derivative of y with respect to x.
Good. And how would we read this symbol?
That's the derivative of x with respect to x is 1. Or just, yeah.
What do you think this is?
Well, that's a constant, so the derivative of a constant is 0.
Good. That's a good answer. So how would you read this symbol aloud?
The derivative of 5 with respect to x is 0.
Good. What's this?
The derivative of 5 with respect to y is also 0.
So notice this is the one case where the variable on the bottom doesn't have to match the variable on the top, because there is no variable on the top. So you can take, now the variable on the bottom doesn't matter. And that should make sense to you. What does this mean, that this derivative is 0? How do we interpret that?
As x is increasing from 5 to 6, the value, well, the function does not increase.
Okay, what is the function?
The function is 5.
That's right. This is a very simple function, but unfortunately we've seen the simplest cases can give students the most trouble. This is a function that's 5. So when the input is 2, what's the output of this function?
5.
When x is 10, what's the output of this function?
5.
All right, when x is pi, what's the output of this function?
Still 5.
Good. How would you interpret this again, one more time?
So the derivative of 5 with respect to x is 0.
How do we interpret that?
As x increases by 1 unit, or as x just increases or decreases, the function does not change.
Normally we would say this tells us that as x increases by 1 unit, the function changes by approximately 0. But in this case, we know the approximation is exact. So we could say that as x increases by 1 unit, the function doesn't change. But as you already figured out, that means that the function never changes. So we don't have to keep saying by 1 unit anymore. In this case, it just means as x changes, the function doesn't change. But we already knew that, right? We already know that as x changes, the function doesn't change. It's a constant function. So we understand why this derivative is true. We don't really understand why this derivative is true. We just memorized it. But this derivative we can understand. And how would you interpret this?
Okay. As y increases or decreases, or as y changes, the function does not change.
So you can see why it doesn't matter what's on the bottom here. Since this is a constant function, when we change x by 1 unit, the function doesn't change. And when we change y by 1 unit, the function doesn't change. Okay. Let's see, maybe we'll go back to this example that we did earlier, y equals cosine x. So one thing you had to do here was you had to, oh, that's not what it was. It was y equals e. Cosine x. So you had to figure out here y prime. So we saw we had to use the chain rule. And here's how we've written the chain rule in the past. And then you went ahead and you worked that out. You wrote the outside like this and the inside. So you made up a new variable u in order to do that. What does u stand for?
U stands for the inside function.
Excellent. That's very good. U is a new made-up variable that we used to stand for the inside function. Okay, now let's try to make sure we understand what these primes here actually mean. So what does y prime mean?
The derivative of y.
Now, as we talked about last time, the one disadvantage of the prime is it doesn't tell you what you're taking the derivative with respect to. You just have to figure out what makes sense for that particular context. But in this case, what were we taking the derivative with respect to? This should be dy over what?
Dx.
Yeah, this problem was in this problem we had to figure out the derivative of y with respect to x because we were going to graph it with y on the vertical and x on the horizontal. So when we've been writing y prime and the chain rule, what we really meant was this. All right, now let's look at this cosine x here. So what are we taking the derivative of here? Well, this term was the derivative of the inside function, right?
Right.
With respect to what?
To x.
That's right. That's why you were able to write that as negative sine x, right? All right. So this term here really meant the derivative of the inside with respect to x. Okay. Now, how about this one? Well, this was our outside function. But what were we taking the derivative with respect to over here? The prime doesn't tell you what we're taking the derivative with respect to, but what have we been assuming we're taking the derivative with respect to here?
To x.
So here you took the derivative of e to the u with respect to x. So you worked out this.
E to the, well.
Think about what you actually did. So the next thing you did is that you wrote down that this derivative was e to the u, right? Using the rule for exponential functions. So what were you taking the derivative with respect to in order to use that rule?
U.
That's right. That's something we haven't really emphasized before, but this prime means something very different from the other primes. You probably said x because the other ones were derivatives with respect to x, but if you think about it, you must have been taking the derivative here with respect to u.
Okay.
Otherwise, you wouldn't have been justified because this is unknown, right? This is unknown. It's only this.
Okay, that makes sense.
That we know. Remember, we can only use our simple derivative rules when the variable up here matches the variable down here. So we haven't been emphasizing it, but this prime really we've been using this to mean the derivative with respect to u. If you go back, remember when we first went over, so what we're using here is the chain rule. Remember that when we first went over the chain rule, I wrote down a 3-step process for dealing with this term. If you go back in your notes, you'll see step 1 was write the outside as a function of u. And then step 2 was take the derivative of the outside with respect to u. If you go back in your notes, you'll see that step 2 of our process was take the derivative of the outside with respect to u. Or at least I hope I said that. I should have said that. Now, I haven't been emphasizing that, so you probably haven't thought about that much. But that's the key here. Since we're taking the derivative with respect to u here, that's what allows us to actually use our simple rules. Okay.
Okay. Yep, it says that.
Okay, good. Now, what does u stand for?
U stands for the inside function.
So would you agree I could erase this word inside here and replace it with
U.
That's right.
Okay.
All right, and one more trick we could use here. We said that y of x, what was y of x in this problem?
Y of x is e to the cosine of x.
Okay, very good. But we actually kind of made up a new function now. We've made up y of u. What's y of u?
Y of u is also e to the cosine. Wait, no, sorry. Y of u is cosine x. Cosine of x.
Now, that was the inside function. That doesn't make sense because notice here we're trying to use u, and your expression had an x in it.
Mm-hmm. Okay.
Maybe this is not really quite obvious, but let's make up a new function which is e to the u.
Okay.
This is basically the outside function.
Gotcha.
Y of x, well, you can basically see this. So we know y of x, well, let me write it this way to show why this is logical. We have y equals e to the cosine x. But now I'm going to replace cosine x and replace that with something else. What could I replace cosine x with? What else equals cosine x in this problem?
U.
Yeah, because remember we said u was the inside function.
Mm-hmm.
So if y equals e to the cosine x, y equals e of u. So notice now we've made y into kind of a new function. Here y was a function of x, but now y is a function of u. And what is y of u?
Y of u is cosine of x.
Well, that wouldn't make sense because then you'd be using x instead of u. Y of u should be a function of u.
Okay, so
what my point was is that we originally had a function y of x. So it had y equals e cosine x. Notice here we've written y as, what variable is y a function of in this equation?
of x.
Yeah, so I could rewrite this line like this to just explicitly show that here y is a function of x. But then we replaced the cosine x with a u. So now this line shows y as a function of u.
Okay.
So now what is y as a function of u?
E to the u.
That's right. So in a way, we've kind of made up a new function. If y of x is e to the cosine x, y of u is e to the u. And the logic there is we know we're using u to stand for cosine x. So we just took out the cosine x and replaced it with the u, and now y is a function of u. Okay, well my point here then is what were we taking the derivative of here? E to the u, right?
Right.
But we just said that's y to the u.
Mm-hmm.
So I can replace outside here with this. So now we have a new way of writing the chain rule. Before we wrote the chain rule like this, but now we've written the chain rule like this. dy, the derivative of y with, dy over dx equals dy over du times du over dx. So I tried to justify each of those steps and explain them a little bit to see how, I'm trying to show how this formula is really the same as this formula, except this formula is a little bit better because it tells us what we're taking the derivative with respect to. So how would you read this term?
The derivative of y with respect to x equals y with respect to u.
The derivative of y with respect to u.
With the u times the derivative of u with respect to x.
All right, so this is another way to write the chain rule. You've probably seen this in the textbook or in class. This is kind of a more standard way to write the chain rule. although I find this is easier for doing problems. But this is a little bit superior because it tells you what you're taking the derivative with respect to. Now, can you see how to... so let me show you some other examples of the chain rule. What would be, say, what could we say would be the derivative of... Well, we could also say the derivative of y with respect to x equals the derivative of y. Instead of using u, we could use a different made-up variable, like w. But then this term would be this. Do you see how this follows the same pattern?
Yep.
All right. Or I could do the derivative of y with respect to q. So do you see how this follows the same pattern?
Yep.
All right. Or I could give up on y and do the derivative of z with respect to h. And I could say that's the derivative of z with respect to w. Do you see the same pattern here? Okay. Okay, so these are all different ways for us to write the chain rule. Okay, so let's solve this problem.
Derivative y cubed respect to x. Well, before we were saying this was unknown.
Okay, good. That's all I wanted to get so far. So can you apply the power rule here directly?
We cannot.
No. But now let's see if we can find a trick that will let us apply the power rule. We don't know the derivative of y cubed with respect to x, but we do know the derivative of y cubed with respect to what?
U.
You're saying we know this derivative?
Well,
remember that we want to apply the power rule. So in order to apply the power rule, what variable do I need to write down here?
y.
That's right, not u. Okay. What would we say is the derivative of y cubed with respect to u? Can we apply the power rule here?
No,
So
we cannot.
that would be unknown. You probably said u because we were just talking about that in some of our previous examples, but this is what we know. So what we're going to do now is we're going to try to use the chain rule so that we can write this derivative like this. So here's how we could do it. We do know the derivative of y cubed with respect to y. So in order to make this a correct expression of the chain rule, what variables should go here?
I guess I'm a little confused because I thought we were doing a chain rule with like y respect to u and then...
Well, actually,
u.
notice we didn't always use u. Take a look at all these examples I did here. What I was trying to show you with these examples is that the things on the top and the bottom could be anything, as long as they follow the right pattern. So what I was hoping here is that we would see the pattern in these examples so that we wouldn't get hung up on the specific symbols. So at first we were doing an example with y and x and u. But then we shifted to totally new letters like z and h and w. The key thing is to see the pattern in all of those examples. So how can I make this equation match this pattern? Say, maybe we could use this pattern here so we're not getting confused by the u. What variables would I have to put here so that this pattern matches this pattern?
I think the pattern is already messed up. I think the pattern is supposed to be different on the...
Okay, well, let's see here. So let's try to see the pattern more clearly. Notice that in this pattern, this variable here is the same as this one.
Right.
And this variable is the same as this one. And these two are the same. Let's see if we can see that same pattern everywhere else. So here we have this variable is the same as this one. And, uh-oh, did I mess? Oh, I might have messed up my beautiful examples here. Let's see. All right, this example I messed up. So when we said we saw the pattern on this one, we should not have said that because I got the pattern wrong. All right, now it matches the pattern. These two variables are the same, these two variables are the same, and these two are the same.
Right.
So I messed that up. Did I get it right over here? Yeah, so here these two variables are the same, these two variables are the same, and these two are the same. That's the pattern for using the chain rule correctly. Notice that you can see, remember that this does not actually stand for a fraction, but you can see why it's tempting to think of it as a fraction, because if this was a fraction, the dw's would cancel, right? If we were really multiplying fractions, and we would just have dz over dh equals dz over dh. So we don't want to actually interpret this as a fraction right now, but you can use that to remember the pattern. We want, if we did interpret these as fractions, we could cancel diagonally and see that the two sides are the same. Here we could cancel the dw's and we could see we have dy over dx on both sides. Or here we could cancel the dx's and we could see we have dy over dq on both sides. Okay, so I do think we can match this into that same pattern. What should these variables be to match that pattern?
Well, the first one should be y cubed over.
I'm not. So these I've already written down for you.
Okay.
So all we have to do is get these two variables.
Right. So my question is, why is it the same variable? Why is it y cubed over y?
Well, they're not exactly the same. Here I have a y cubed and here I have a y.
All right.
So notice how these match, just like we said they were going to match over here. So I guess the reason why we're having trouble seeing the pattern here is before, I always put just a single variable on top. But remember, a single variable could stand for anything. So this dz here might stand for a great big expression. So we can still follow the same pattern that we had before. Whatever is in this position should match whatever is in this position. Well, that matches what I've already written here to start off with. I wrote a y cubed here, and I wrote a y cubed here. And then I just told you what the convenient variable for this to be was. So now, following the earlier pattern, we should be able to write down these two variables.
Okay. Y over x.
Okay. And do you see how that would, if we pretended these were fractions, the dy's would cancel, and you would get back dy cubed over x. They're not really fractions, but that's a memory aid to see that we're getting that expression right. Okay, so the thing that was giving us trouble here is that in the earlier examples, I just wrote a single variable in this position, and here I wrote an expression, but we can still follow the same pattern. All right. Now, why is this helpful? So this is the chain rule. Now, why is this helpful? Well, can we apply the power rule directly to this expression?
We cannot.
Can we apply it to this?
Yep.
So what would that give us?
3y squared.
Okay, good.
Times dy over dx.
Yeah. There's no simple way to simplify that. We already saw earlier, there's no simple way to simplify dy over dx. So we just leave it like this. Okay, so now we've shown another application of the chain rule. So what do you do when the variable on the top doesn't match the variable on the bottom? When the variable on the top doesn't match the variable on the bottom, what do? You use the chain rule to evaluate the function. When these two things don't match, we use the chain rule to evaluate the function. Let me show you another example so we can get the hang of that.
Okay.
Okay, so can we apply the power rule directly to this function?
Nope.
No. So what do we want to do? We want to rewrite this as something that we can take the derivative of. So what do we want this variable down here to be so we can apply the power rule?
Y.
But these two things are not automatically equal. So the only way we can do this is by applying the chain rule.
Right. So y over x.
There you go. Good. So the advantage of the chain rule is that it lets you change the variable that you're taking the derivative with respect to. This allows us to change the variable we're taking the derivative with respect to. Good. And then the left-hand side would be?
5y to the fourth times dy over dx.
Okay. That's good.
Yep. Okay.
All right, good. Okay, so try this problem.
Okay. So that's going to be 6y times dy over dx.
Let's try this on your screen and try writing it out in, write out the same steps that we used before. Let's not skip any steps. Try writing out each step that we need, like we wrote down in the previous examples, without skipping a step.
Okay.
Okay. What's the justification for the first line you wrote down?
This first line is chain rule.
Good. Read that aloud. How would you read that aloud? The first line?
The first line is the derivative of 3y squared with respect to x equals d 3y squared
Well,
over
let's
y.
not read it as d. Let's read that aloud too.
So the derivative of 3y squared with respect to x is equal to the derivative of 3y squared with respect to y times the derivative of y with respect to x.
Okay. Now, one of those terms you didn't write the same as the other terms. There's a problem with our notation for one of those terms. Yeah.
Yeah.
If you leave out that d, that term becomes meaningless. Remember that the d on the bottom, we've been interpreting that as with respect to. I think that might have confused you later on because it made it look like you were dividing by y. But we're not dividing by y. Remember these fractions aren't really fractions. They don't really stand for division. They stand for taking the derivative with respect to another variable. Okay, so that's why I wanted to practice that notation. It's important for us to have good notation for those problems. Okay, what was the purpose of taking the chain rule? The advantage of it is that it allowed us to use the power rule in the next line. We could not use the power rule until the variable on top matched the variable on the bottom. Good. And when you're ready, I'll go back to my screen.
Okay.
So let's try this problem. Let's try writing this out.
Okay.
Excellent. Good. So we could not use the rule for the derivative of sine until we got the variable on top to match the variable on the bottom. So first we had to use the chain rule, and then we could use the rule for the derivative of a sine. Good. How can we check that you wrote the chain rule correctly? Well, remember they're not really fractions, but if you pretend that those expressions are fractions, what would happen to, how could you simplify the right-hand side of that first line? If that really was a fraction, how would that simplify?
We could just write it as sine.
That's not really what I was going for. I guess I'll go back to my screen. How does this simplify?
It's 1.
Oh, actually, it's not. Maybe take your time. Do you remember how to deal with fractions like this? Do you know how this simplifies?
We can cancel the x and the x.
Well, there's only one x.
Oh, okay. Oops.
What can we cancel?
The a's, it's x over y. I was reading that incorrectly, I guess. Yeah. So this will simplify to x over y.
That's right. Okay. What does this simplify to?
C over w.
Good. So over here we wrote so these are not really fractions. But if we pretended they were fractions, what would this right-hand side simplify to?
The derivative of sine of y over, well, with respect to x.
Or just d sine y over dx,
Yeah.
which matches the left-hand side. I'm just trying to give you a memory aid to make sure you're using the chain rule correctly and to show why this notation is attractive to the mathematicians. These are not really fractions, but if we treated them like fractions, we could see that this really is a true equation. It would be a true equation if we treated them like fractions. This expression really does equal this expression, just like this really equals this, and this equals that. So that's just supposed to be a memory aid to help us to make sure that we're writing this correctly. For example, would this be a correct way to write the chain rule?
No.
Because these two variables don't match, so
Right.
they wouldn't cancel. Would this be a correct way to write the chain rule?
Yep.
Because these variables matched, so they could cancel, and that would give us back here if we pretended they were fractions. Would this be a correct way to write the chain rule?
Yep.
Because these two.
I know it would. Well, I guess so, if you're not trying to use the power rule.
Okay, that's a good answer. This is a correct use of the chain rule, because these variables would cancel. It's correct, but it's not useful. It's not useful because we want this variable also to match what's on top. So notice these two variables here could be anything. They could be u and u, or they could be w and w. Any of those would match the chain rule, but what variable is it useful to put down here?
Why?
Because we want this to match what's up here. And then what would this variable be?
Why?
Good. So earlier, I think, when we were first going over this, I think you were tempted to think we were going to use a u here, because we'd used u in some of our previous examples. But this doesn't have to be u. It can be any variable, as long as these two variables match diagonally. And how do you know which one to use? Well, you want to use a variable here that matches this variable here, so we can use our simple rules for derivatives. Okay. Okay, what's this?
3x squared. It's going to be 6x times dy over
I
dx.
think you might be overcomplicating that. So are you trying to use the chain rule for that?
Yep.
Okay. Well, if you were going to use the chain rule here, so there's two ways to see that. First of all, we could have written this as Why are you using the chain rule? You're probably using the chain rule because you're saying these two variables don't match, right?
Right.
Well, what is y? What could I plug in for y?
3x squared.
Now the variables do match.
Mm-hmm.
So what's this derivative?
6x.
Notice there's no need for the chain rule.
Right. Well,
Or you could think about it this way. If you were going to use the chain rule, how would you write it out? Well, you would have, what variable do you want to have on the bottom here?
y.
And then what variable would go up here?
Y.
And how about here?
X.
If you think about it, this doesn't really match our previous examples, but do you know what is dy over dy?
1.
Yeah. Notice how that just took us back to where we started.
Mm-hmm.
So this is actually not a great candidate for using the chain rule here. What you were saying is that you have to use the chain rule in order to get the variable on the top to match the variable on the bottom. But actually, you don't have to use the chain rule to get those variables to match. All you have to do is plug in 3x squared for the top.
Okay.
This is what we've been really doing all along without actually explicitly saying so. This is just a normal derivative, right? This is just the normal derivative that we learned how to do on the mastery test. Sometimes when people learn a new technique, they forget how to use the old techniques. So this is just a normal derivative like we've been using in the past. Y here stands for 3x squared. So in order to get the variable on top to match the variable on the bottom, all we have to do is just plug in for y. And we got this.
So before, when we were saying that was unknown, we could have really just said it was also 6x.
If we knew what y was.
Okay.
So when we said this was unknown before, I can't see where I wrote it down anywhere. Here. When we were saying that these things were unknown, we meant they're unknown if we can't plug something in for y. Until we've plugged something in for y, it's unknown.
Okay.
So in this case, we don't need the chain rule. When do we need the chain rule? Because we could just plug in for y. The cases where we've been using the chain rule before here had been noticed when we had things like 3y squared on the top, or y to the fifth.
Oh, okay. Yeah, that makes sense.
Here's where we've been using the chain rule when we had a function of y on the top. Although even here, theoretically, we could have plugged in for y if we knew what y of x was. So what's this?
$18x squared.
Do we need the chain
Sorry.
rule?
Nope.
Technically, you can see that what you're doing here is this. We haven't been writing it out this way before, but what you're really doing is this. Can we apply the power rule here?
Mm-hmm.
Yeah. So the chain rule is a way to get the variable on top to match the variable on the bottom. But here we didn't need the chain rule for that. We could just use simple substitution to get those variables to match. Good. This problem is a little bit different than the ones we've done before. We need to adapt a little bit. Can you think of any way to solve this problem?
Okay. Could rewrite y as y equals 3x squared minus 2x.
Excellent. Good. That's a very good idea. Then what?
And then we can substitute 3x squared minus 2x into the top. So we can rewrite it as d parentheses, or like that, 3x squared minus 2x. And then we can just find the derivative of that, and it's 6 x minus 2.
Excellent. Great. Very good. So we never actually done a problem quite like this, but it wasn't super hard once you saw the trick. So the point is, it's if you're going to take the derivative of a function of y with respect to x, what we want to do is plug in for y. We need to know what y is. Well, all of the problems we've been doing earlier, I just told you what y was. Here I told you y is 6x cubed. Here I told you y was 3x squared. So it was easy to plug in for y. But here, this problem is a little bit more difficult because I gave you an equation, but the equation didn't tell you directly what y was. But you figured out what you needed to do. You had to solve the equation for y. Once you had solved the equation for y, then we could just plug in for y, and now the variable on the top matches the variable on the bottom, and we're able to figure out the derivative. Okay, so the point is, if you're not told what y is, you can solve for y and work it out. So how would you work this out?
Okay, we could use a similar process. We could rewrite it as y equals sine of x minus 5x. And then we can substitute that into the top. And we can rewrite that as d parentheses sine of x minus 5 of x over d of x. And then that's equal to the cosine of x minus 5.
Excellent. Good. Notice that you really do have to solve this for y first. If a student didn't solve for y first and they just tried to take the derivative directly, they might think that this was positive 5. But when we moved it over here, we found that it ended up being a negative 5. At least it's best to solve for y directly.
Mm-hmm.
Now let's discuss this problem. Any ideas about how we could go about approaching this? What do we need to do here?
Well, we could, well, we were solving for y before.
Yes, good.
But I guess.
Okay, good. But it would be difficult or impossible to solve this equation for y.
Right.
I suppose technically it might be possible using the quadratic formula, but it would be quite difficult to solve it for y. In fact, let me write it like this maybe. Now I think it's just about impossible to solve for y. So sometimes the problem is, what we've been saying is if the equation is not solved for y, the first thing you do is solve it for y and then plug in. But some equations are difficult to solve for y, and some equations are impossible to solve for y. So what do you do then? Well, for that we need a new technique, and that's what we've been working towards all this time. How do we deal with this situation? We use a new technique that's called implicit differentiation. So let me show you how implicit differentiation works. So here's the question. So the first trick here now is I'm going to take the derivative of this equation with respect to x. So here we go. We've taken the derivative of this here with respect to x. Let's see.
Okay.
One second. Let me see if this is actually going to work. Okay. Is that legal? Well, remember that the golden rule in mathematics is you can do anything you want to the left-hand side of the equation as long as you do the same thing to the right-hand side of the equation. That's the basic rule of math. You can do anything to the left if you do the same thing to the right. So is it legal to take the derivative with respect to x of the left side of this equation? Well, yes, as long as I do the same thing to the right side of the equation. So this step was legal. Now, it's not really clear yet how this is going to give us the answer, though, because we want dy dx, and I don't see any dy dx here. But let's try to simplify things. How could we simplify this left-hand side? Well, we could use the sum rule. Do you see how I got from this line to here? Mm-hmm. Because the derivative of a sum is the sum of the derivatives. And what about the right-hand side?
We could rewrite that as d sine of x over dx.
Good. Although that's basically what we already had. Is there anything else you could do to simplify the right-hand side?
We could just rewrite it as cosine of x.
Yeah, you may as well just take that derivative. Okay. How about this? Can you simplify this term?
Yep, that's 5.
Good.
And then now for the left side, well, I guess we can't cancel anything out yet.
All right, now how about this term?
That term we can rewrite as 1 plus dy over dx.
Let's see, where did you get the 1 from?
I was, yeah, that is.
Remember, what was the question asking us for?
What can we rewrite that as?
What was the original question? What are we trying to figure out?
Oh, okay.
What are we trying to figure out?
The derivative of y with respect to x.
So this is what we're trying to figure out.
Right.
So we don't want to replace this with anything. Our whole goal, now you can see why this was a good trick, because it did introduce what we're trying to figure out into the equation. So all we have left is we have to simplify this term.
Okay. So that term, we could rewrite that as dy to the 4th over y times dy over dx.
Okay, excellent. So the important thing is that you didn't just try to apply the power rule like we did here, because the variable on top doesn't match the variable on the bottom. That's the point of all the work that we've been doing so far, to see we can't apply the power rule yet to here because the variables don't match. All right, now what?
Okay, so now we can cancel out dy from the bottom and dy from the top on the left and middle terms. So we can rewrite that as dy to the 4th over dx plus.
But isn't that what we just had a second ago?
That
would just be reversing the previous term. I think I confused you there by something I'd said earlier. I said that that to make sure you've written the chain rule correctly, you can imagine what would happen if you canceled these dy's. If you did cancel them, you would get back to what you started. That just confirms that we wrote the chain rule directly. It's not something we actually do to solve the problem. I think I confused you by talking through that. Remember, these aren't really fractions. It was just, if you pretend they're fractions and pretend you were canceling, you can check that you've written the chain rule correctly. But they're not really fractions, and we're not really going to cancel them. As I might have confused about what I expressed there. But anyway, it would be pointless to cancel because that would just take us back to what we had a second ago. So is there anything else we can do to simplify this?
Yeah, okay. Yeah, we can rewrite the left-hand term as 4y to the cube.
That was the whole reason why we'd use the chain rule in the first place. The whole reason we would use the chain rule was to get these two variables to match so that we could use the power rule. These two variables don't match, so we can't use the power rule, but now that they do match, we can use the power rule. Good?
So 4y cubed times dy over dx plus dy over dx plus 5 equals cosine of x. And then I guess what we want to do is try and isolate dy over dx.
Because that's what we're trying to solve for. Excellent.
Right. So we could rewrite dy over dx plus dy over dx equals, so, oh, okay. Okay, yeah. dy over dx equals cosine of x minus 5 minus parentheses 4y cubed times dy over dx.
That's right. But now you'd have a dy over dx on two different sides of the equation.
Okay.
That doesn't help us with the algebra. So what we actually want to do here is, so do you see how I got this line?
Mm-hmm.
Now you could move this term to the right, but that wouldn't help us to solve for dy over dx. Actually, the next trick here would be to factor.
Okay.
And then what goes inside?
That will be 4y cubed plus dy over dx.
Now,
Oh,
careful with your factoring.
So we took
Oftentimes people don't know how to factor this. How would you check this? You would check it by using the distributive rule, right? Dy over dx times 4y cubed really would get us back to here. So what does this number have to be so that this times this equals this?
1.
Something that might have helped you here is the reason you had trouble factoring is because you didn't see what this was being multiplied by. But it really is being multiplied by 1, isn't it? If you write it that way, it might make it easier for you to factor that. And then what?
Okay. Okay, so now we divide both sides by 4y cubed plus 1. And that will get dy over dx by itself on the left. And we have dy over dx equals cosine of x minus 5 over 4y cubed plus 1.
Okay, what was the question asking us for?
Dy over dx
So
equals
we're done.
question.
Okay, so that's the technique of implicit differentiation.
Okay. Cool.
So it puts together a lot of the different techniques that we've talked about. One thing that should look a little weird to you about this is in the past, whenever we took derivatives, we ended up with the derivative was just a function of x. But here the derivative has both an x and a y in it. We've never seen that on any of our previous answers. If possible, it would be nice to get rid of the y by substituting in for y. But remember, that's what we don't know how to do on this problem because the original equation is impossible to solve for y. This equation is impossible to solve for y. So one thing that will be different in our answers now is that we're going to have both an x and a y, typically, in the answers. We won't be able to get rid of the y. By the way, would you agree another way to write this would be this then?
Yep.
Yeah. What does this prime stand for? Well, it stands for derivative, and in this case, the derivative with respect to x. So if the question had asked us for y prime, we would solve it exactly the same way. And we just have to know that what they meant here was the derivative of y with respect to x. Okay. Okay, so let's go through this problem together.
Okay.
So again, the most natural thing to do here would be to solve this equation for y. But again, this equation is so complicated, it would be difficult or impossible to solve it for y. So what do we do instead?
So we can't solve for y, so we have to...
So we'll go through this one together. We're going to have to use implicit differentiation again. And remember, the first trick here is to take the derivative of both sides with respect to x. Remember, is it legal to take the derivative of the left side with respect to x? Well, sure, as long as we do the same thing to the right-hand side. So that's the first step of implicit differentiation. The first step of implicit differentiation is to take the derivative of both sides with respect to the variable that you want to take the derivative with respect to. Now, it might seem like this is not helpful because we don't want this. We want dy over dx. And so far, we don't have any dy's over dx. But we saw from our previous example that eventually the dy over dx will pop up. So we'll trust that that will happen again here. So let's try to write this down step by step like we did previously without skipping any steps. So what's the first step thing I can write down to simplify this left-hand side?
We can use the sum rule
Yes.
and rewrite that as dx cubed over dx plus 3xy over dx plus y cubed over dx.
Now, you haven't quite been saying that correctly. Remember, we're taking the derivative here. So this is not 3xy over dx. It's the derivative of 3xy over dx, or d 3xy over dx. And then the next term is
dy cubed over dx.
Good. In the past, we haven't usually written out the sum rule because it's been so simple we did it in our head. But for implicit differentiation, it's probably safer to actually write it out. Okay? And what do we write on the right-hand side?
6.
How did you get that number?
The derivative, it's 0.
Yeah, that's the constant rule, right? That's the reason why. This is, again, a case where the simplest examples give people the most trouble. So that's why we were doing this exercise here for trying to understand why the derivative of a constant with respect to a variable is 0. That's one that oftentimes messes people up. All right. Remember that your first instinct was to say that this was 6. So you were saying that the derivative of 6 is the same as 6. But remember, there's only one function that's the same as its derivative. What's the only function that's the same as its derivative?
E to the x.
Right, and this certainly doesn't look like e to the x. So we must be making some mistake if we say the derivative of 6 is the same as 6. Okay. All right, now how can I simplify this term?
We can rewrite that term as 3x cubed.
Say again?
3x cubed.
What number do I put here?
2.
So that would be 3x squared.
Squared.
Okay. And how about this term?
We can, well, we're trying to find dy over dx. So I'm not sure.
This is a little different from the previous example. Now we need to simplify this into something we know how to take the derivative of. So do we know any simple rules that would take the derivative of this? Well, no, this expression is too complicated. So what could we do to simplify it? A simple rule we could use to simplify this is the product rule. How would we apply the product rule to this?
Three xy. 3x times y plus.
So let's write down what the first. Let's not do any of it in our head. If we were going to write down the product rule, how does the product rule apply to this? Maybe it would help for me to write it like this. Do you see how this is the same expression as we had before?
Squared.
So, first of all, I've simply rewritten this expression. Do you see how this is the same as what I had before?
Yeah.
But hopefully now it should be more straightforward to apply the product rule. So how would the product rule apply to that? And what would be the very first step to write down to apply the product rule?
We could write parentheses 3x prime times y plus y prime times 3x.
Good. Except on these implicit differentiation problems, we're not using primes. We're using a different derivative notation because we have to be very careful now about what we're taking the derivative with respect to.
Okay. So
what does 3x prime really stand for in this notation?
It means d3x over dx.
Because that's dx is what the variable we're taking the derivative with respect to. Good. How about this term? How could I rewrite this without the prime?
That would be dy over dx, which is what we're trying to solve for.
That's right. So that's okay. So this gave you trouble, but you know the product rule, but you've never written the product rule using this d over d notation. So this is the first time I used the product rule using this d over d notation. Just like we had to learn how to use the chain rule in the new notation, we have to learn how to use the product rule in this notation. Okay. And then we also have this term.
Okay. That's wait. Huh. That's just the same as I believe. So dy cubed over dx.
So you're saying there's no way to simplify that?
Oh. Okay, so we could simplify it as dy cubed over y times dy over dx.
So
sorry, that y should be dy.
Good. Okay. Yes. Why do we not want to just leave it like this? Well, we don't want this in our answer, right? Remember, we're trying to figure out this, so we need to get rid of everything that we don't want in our answer. You can't. Why couldn't you just apply the power rule over here like you did on to this term? This term you just applied the power rule to. Why can't we just say this is 3y squared?
Because it's not with respect to y.
That's right. Good. These two variables don't match. That would be a common mistake. So it's good that you saw we couldn't do that. Okay, good. That equals 0. All right, so what's our new line?
So our new line is 3x squared plus 3 times y.
Good. Now we can apply the power rule, because now the variable on top matches the variable on the bottom. Good. Then what?
Plus plus dy over dx times 3x.
This we don't want to simplify away because this is what we're trying to figure out. Good.
Plus 3y squared.
Now we can apply the power rule because now these variables match. Good.
Times dy over dx equals 0.
Okay, good. Now, so let's review where we are so far. Notice that the key thing that was giving us trouble was this term. And remember that the way we simplified it was by using the product rule. That was the key step that was giving us trouble. Can you see how the product rule helped us? Because we didn't have any simple rules to take this derivative. But the product rule allowed us to separate the x and the y. So basically, we don't have any simple rules that will take the derivative when there's two different variables on top. We don't have any way to take the derivative when there's two different variables on the top here. So we need to use some kind of simplification. By using the product rule, we were able to separate the x and the y into separate terms. That's why the product rule was helpful here. Remember that originally this was just written as 3xy. What really helped us to take the product rule was when I put in some parentheses here to see that this is really two things being multiplied by each other. Okay, now what?
Okay. Let's see. I guess we can simplify further by writing 3x squared plus 3y plus dy over dx times 3x plus dy over dx parentheses 3y squared times 1. I guess that doesn't make any difference.
It seems like you pretty much almost just rewrote the previous line.
Yeah, I don't know.
So what's our goal now? What are we trying to do?
Solve for dy over dx?
Yeah, so notice now we're done with the calculus. It's now turned into a high school algebra problem. But unfortunately, most people's high school algebra is not that strong. So, but so far, previously in the course, we never had to really use much algebra. But for these problems, we have to go back and review our high school algebra. We need to solve this equation now for dy over dx. So the first thing we have to do is get everything that's not a dy over dx on the other side. So we could move this 3x squared to the other side.
Can we just move it all at once?
Well, we could also move the 3y to the other side. Can I move this 3x to the other side? Well, this one I can't move yet. Do you see? Because it's connected to the dy over dx.
Right.
And can I move the 3y squared to the other side? Well, I'm not ready to do that yet either because it's connected to the dy over dx.
Okay.
Of course, you could move this whole term to the other side, but that would be a step backwards because we want all the dy over dx's on the same side of the equation. We could write this. That would be legal, but it wouldn't be helpful because now we'd have a dy over dx on two different sides. Now what? Remember, we're trying to solve for dy over dx.
Well,
so what's our problem? Well, the problem is we have two dy's over dx, and we need to simplify so we only have one dy over dx.
so we can factor.
So we're going to use the same trick that we used previously, which is factoring. That's right. So what goes in here?
3x plus 3y times 1.
3y squared.
3y squared.
There's not really too much need to say times 1 because times 1 doesn't change anything.
Okay. All right, so now we can divide by dy over dx. Right now, so we divide by 3x plus 3y squared. And that isolates dy over dx, and then we get an answer with x and y. So now we can rewrite that as dy over dx equals negative 3x squared minus 3y over 3x plus 3y squared.
Okay. You could simplify a little bit more by canceling the 3's, but this is good enough. So here's our answer. Notice that this answer is a little different than the derivatives we calculated before because it has both an x and a y in it. But there's no way for us to get rid of this y because we couldn't solve for y in the original equation. All right, so that's our second example of implicit differentiation.
This is somewhat tricky, I guess. But I don't know.
Yeah, it turns out that there was a lot of different things we had to go over before we could start to understand the basic method here. Okay, well, so we've gone through two examples together. So let's see if we've got that down. Why don't you try working this one out on your screen?
Yeah. Solving for y. So
Let me give you a simpler example for you to start with on this. Let me write down this equation instead. Let's start with this example.
okay.
Okay, so it looks like what you're trying to do is solve the equation for y.
Mm-hmm.
All right, that's an excellent technique. So that's good that you saw that you could do that. That's right. You could just solve this equation for y, and what would you do then?
We take the square root
Yeah.
of both sides.
So what's the next step? I guess you can write down your next step. Good.
Square root of, well,
Now, the square root of a sum is not the sum of the square roots. Now, the line you're erasing is correct. It was the next line where you were making a mistake. So the line here, you just took the square root of both sides. That's certainly legal. But then it looked like you said the square root of 25 is 5. It looked like you were going to take the square root of 25 and then the square root of negative x squared. But the square root of a sum is not the sum of the square roots.
okay.
So you could just leave it the way it is.
Okay.
And then what would you do? You can just describe in words what you would do.
I'm not exactly sure, so I'm not sure.
Okay, so this is an example of how when people learn new stuff, sometimes they forget how to do the old stuff. This is a derivative that we did on the mastery test. Now,
I'm not,
so what you've done is you've succeeded in solving for y. Y equals the square root of x squared plus 25. That was one of the types of derivatives that you learned how to do when you were doing the mastery test. So basically, maybe you don't realize it, but what you've done here is you decided not to use implicit differentiation on this problem. Instead, you decided just to solve for y and find the derivative directly using the same techniques we used for your mastery test. And that's fine because this equation can be solved for y.
How can we not use implicit differentiation if the variables are different? That's what.
Okay, maybe this is the thing that was confusing us earlier. So you're saying that y is not the same as x,
Right.
but what is y equal to?
Y is equal to square root of x squared plus 25.
So plug that in for y. Actually, yeah, that's right. So let's plug that in for y. Now you're still taking the derivative, so you can't get rid of the d. We haven't taken the derivative yet. We're just plugging in for y. All right, now the variables do match. So now we can use the same techniques we used on the mastery test. Okay, now we don't want to mix up those two notations. You've gone to the prime notation, so we should get rid of the dx on the bottom. We can use the prime notation or we can use the d over d notation, but we can't use them both at the same time. Actually, you don't need to erase the whole thing. We've learned how to use the chain rule using the prime notation, so it's probably best to stick with your prime notation and get rid of the dx on the bottom. The d over d notation is useful when you're doing implicit differentiation, but we decided not to do implicit differentiation here. We're just going back to the same techniques we used for the mastery test.
Okay.
Okay, good. Okay, so we ended up not using implicit differentiation here. Here you could just solve for y. Now, one thing that messed us up here was, remember at first you were saying that you didn't know how to find d, even after you solved for y, you were saying you didn't know how to find dy over dx. But do you see why I was saying, actually we just ended up using the same techniques as from the mastery test? What was worrying you was you were saying, well, gee, the variable on top doesn't match the variable on the bottom. But you could get them to match by just plugging in for y, right? That was the whole reason why you'd solved for y. If they're just asking for dy over dx and we know what y is, then we can plug in for y and we can get the variables to match in both places. All right, why don't you go ahead and rotate your screen so it's rotated, right? Good. Okay. Now, so now we've gotten an answer. But remember what we were actually trying to practice here in this chapter, in this section, is implicit differentiation. So on this problem, even though you don't need implicit differentiation, let's also practice that technique. Hopefully you have enough space left here to do that. Remember we've already done a couple examples of implicit differentiation together, so let's try to go through that. How would we apply the implicit differentiation technique to this problem?
Okay. So we're trying to, if we can't solve for y, then we would
Okay. Now let's improve that notation a little bit. It doesn't make sense to have the y's. It shouldn't. The d's should just be by themselves. So it should just be
Hmm.
d over dx on the left and d over dx on the right. Because what are you doing? You're taking the derivative of the left-hand side of the equation and setting that equal to the derivative of the right-hand side. How would you read that right-hand side aloud? How would you read what you have now on the right-hand side?
The derivative of x squared plus y squared with respect to x.
That's the left-hand side. Okay, good. That's right.
Okay.
Notice how you couldn't read that if you had dy on the left-hand side. Then it would be meaningless, right? Then it would be the derivative of y, x squared plus y squared with respect to x. That doesn't really mean anything. And how would you read the right-hand side of your equation aloud?
The derivative of 25 with respect to x.
Notice it doesn't make sense to say also have a dy there because you're not taking the derivative you're not taking the derivative of y. You're taking the derivative of 25. Now, why did you put in the y? Well, ultimately, we'd like to know what dy over dx is, but we haven't gotten that yet. Okay, so now what?
Can use the sum rule to break this up. X squared. And this is just going to be 2x and
One moment.
no.
I'm not sure how you're getting that last line. What was your thought process there?
I'm trying to get rid of this square root. I mean, this square of dy
Okay,
over
yeah.
dx.
So what you have is d of y squared over x. Can we apply the power rule to that directly?
We cannot.
No. But we have learned, because the variable on top doesn't match the variable on the bottom. But we've learned we've learned what the technique is to deal with that type of situation when the variable on top doesn't match the variable on the bottom. And it's probably better not to start rearranging the equation until we've simplified more completely. So let's leave the 2x on the left-hand side for the time being.
Okay.
Good.
Okay, so now these cancel. So no, that just gives us the same thing. Okay. Now now we can rewrite this. Okay.
Okay, so we finished that off. Okay, good. So we had some trouble with a couple of the steps, but we got to the right answer. I think I must have really confused you when I talked about the technique where you imagine canceling those dy's. Remember that in the d over d notation, they're not really fractions, so we never really cancel diagonally. My point was only that that's a way to help you remember that you've done the chain rule correctly. I guess it's kind of a subtle idea. If you pretend that they're fractions for a moment, and ask what would happen if you did cancel diagonally, you can see that you would get back to your original dy squared over dx. That's just a way to confirm that you've written the chain rule directly. But in fact, they're not fractions, and we shouldn't cancel diagonally. That's just a trick to make sure that we've actually written the chain rule correctly. Instead, remember the whole reason we used the chain rule was so that we could use the power rule. And that's what you did when you thought about it correctly. Once you've got dy squared over dy, now you can use the power rule because the variable on top matches the variable on the bottom. So what do you do when the variable on the top of the derivative doesn't match the variable on the bottom of the derivative?
You can... Oh, I'm not sure if I'm going to word this correctly, but
I guess what I was going for is you use the chain rule.
Okay.
None of our simple derivative rules work directly. Or something else you could do is just plug in for the top so that they do match. That's what we did on the left on your screen. Sometimes we can just plug in for y so the variables do match. Like on the left, we plugged in square root of x squared plus 25 for y, and then we didn't need the chain rule. But if you can't do that, then you can just use the chain rule. Okay, I'll go back to my screen. Maybe this was a little confusing because we ended up doing the problem two different ways. The first time we just solved for y and took the derivative directly, and we got that, if you remember, what we got when we did it the first time was this.
Mm-hmm.
But what did we get as the answer when we used implicit differentiation? When we used implicit differentiation, we got this. It might seem like these two answers contradict each other. In fact, do they contradict each other? Let's see. Oh, I didn't write this down correctly. What you actually got in the first method was this. There was also a 2x term. Okay. But you can see they're actually the same because remember that you actually saw that you could solve for y here. You got that y was square root of 25 minus x squared. This should have been a negative. So this would be square root of 25 minus x squared. Okay, and this 1/2 cancels with the 2. So anyway, I'm just pointing out that we got the same answer both ways, even though they didn't look the same. Because what does it mean if you raise something to the negative 1/2 power? So this is just the same as 25 minus x squared to the negative 1/2. So you can see these are the same. 25 minus x squared is the same as negative x squared plus 25. So if you do enough plugging in, we can see that we did get the same answer in both cases, even though it's not obvious. Okay, now from now on in this chapter, we're not going to be using this method. Even when it's possible to solve for y, that's usually not the simplest approach for the types of problems here. Instead, we're going to be using this implicit differentiation technique. That's what we're trying to practice here. But it was good to see that in this case, we could do it two different ways. Okay. So let's go back to the problem that I had written down before. Well, no. Let me give you this. let's do this one first. Let's try this.
Okay. Okay.
Okay, yeah, so there was a mistake there. That's good that you caught that. Let's scroll back up again to see where that mistake came in. So, how did you get your third line there? What's the justification for your third line?
Um, for the third line, we use the sum rule.
Or the difference rule? Good.
Right.
What does that rule say?
Uh, we can take the derivative of the parts of the term of the expression, and it's equal to the expression.
And then subtract them. Yeah.
Right.
But notice how originally you hadn't actually been doing that because you weren't taking the derivative of the y cubed. You had written down something that actually was kind of meaningless because you had written down y cubed over dx, but that's kind of meaningless because remember dx doesn't have any meaning by its own, on its own. It only means something if we're using it as part of a derivative. Okay. Now, how did you get your 10?
10 is 5x cubed. It should be 10x.
Good.
Okay.
By the way, let's just go over the terminology. How would you read that 5x to the 2? How is that read aloud?
5x2. This is the derivative of 5x squared with respect to x.
Good. I just wanted to point out, I noticed that oftentimes you read that as 5x cubed, but that would be to the third power, right?
Right.
All right, so we should read that as 5x squared. Okay,
5x
good.
squared.
Okay, so we had taken that derivative incorrectly. How did you get your 12?
12 is the derivative of 3x to the fourth with respect to x. So this is totally wrong. This is frustrating. Okay, this is... Okay.
And let's fix the 10s too. Okay, so that's the material from the last mastery test. Unfortunately, the natural thing that happens to students a lot is when they start learning new material, a lot of the old material, they start to misremember it, even if they understood it quite well before. I know before we were getting those derivatives right quite well, but unfortunately sometimes it's easy to start forgetting the old stuff when we're trying to process new stuff. So we have to hold all of that in our mind at the same time. Okay, so now we can continue.
Okay. Okay. Derivative of y cubed is 3y squared. Okay.
Okay, so we ended up with the right answer. So that's another example of the use of implicit differentiation. So we had a couple of difficulties there. One difficulty is remember that when you're doing the derivative notation, you have to remember to put in both d's. When we're using derivative notation, we have to remember to put in both of those d's. We hadn't used that notation in the past, so that's a new notation that we have to get comfortable with. In the past, we used to use those primes, so now we need to get used to that new notation. And also, we have to remember to keep correctly doing the derivatives from the mastery test. It's easy to start forgetting some of those techniques. All right, so we ended up with the correct answer here. On my screen, I've written down a problem, so when you're ready, we can start by trying that problem.
That's 5. Okay, so this is just 15 squared. Okay.
Okay, good. How would you read that expression aloud?
The derivative of 5x cubed with respect to x is 15x squared.
Okay, fine. Right, that's correct. So we've already gone over how to try that type of problem, so I'll write down another type of problem. Now let's try this problem.
Okay.
Okay, good. So the key thing I wanted to go over with you is we've been discussing that we can only use, so in the first problem that we did, 5x cubed, you used the power rule. And what we've been discussing is that we can only use those simple rules for derivatives when the variable on the top of the derivative matches the variable on the bottom of the derivative. So what do you do when the variable on the top doesn't match the variable on the bottom, like the second problem I gave you, where you had dy over dx? Well, there's actually two different solutions that we've gone over that I wanted to make sure were clear. One solution is you can plug in something different for the top. That's what you did here. Since your top variable didn't match your bottom variable, you plugged in something different for the top. Instead of y, you plugged in 3x squared, And then you could use the power rule, because once you've done that, the variable on the top now matches the variable on the bottom. Okay, so that's one thing that you can do when those variables don't match. So that's good notation. It's probably better when we have an expression on the top to put it in parentheses. So let's go ahead and do that for your notes. D parenthesis 3x squared parenthesis. To show that we're taking the derivative of that whole expression. Good.
Okay.
I'll go back to my screen. Now let's try this problem.
Okay.
No, that's not quite what I wanted. Let's try this problem. So this is a separate problem, separate from the previous one.
Okay, so okay.
Okay, good. That was a good method, and it's good that you knew when to stop. So you ended up with an expression that has dy over dx in it. It would be tempting to try to simplify that further, but I didn't give you enough information to do that. So it's good that you saw that there was nothing more you could do to simplify that dy over dx. You just had to stop at that point. But that shouldn't worry us too much, because remember, one of the main applications for these methods we're going over here is implicit differentiation. And when you're doing implicit differentiation, it doesn't bother us to have a dy over dx in our expression, because that's what we're trying to solve for anyway. We have to get rid of a complicated expression like d3y squared dx, but we don't need to get rid of dy dx. Okay, good. Now, do you see how this compares to the previous example? How is this similar to the previous example with the y equals 5x, y equals 3x squared? Well, there's one way they're similar. Notice that in both cases we started with different variables on the top and the bottom of the fraction. I think I'll go back to my screen. So in the previous example, we started with y on the top and x on the bottom, two different variables. And in this example, we also started with two different variables. But what I wanted to show you is that there's two different tricks to deal with that. If you have a different variable on the top and the bottom, then obviously there's two things you could do to fix that. One thing you could do is change the top variable. Like we did here, we changed y to x. And the other thing you can do is change the bottom variable. That's what you did. By going through this step. So notice those are the two logical things you can do when these two variables don't match. Since the top and the bottom don't match here, we rewrote the bottom so that it had a y. That's what we did with this expression here. Now there's a y on the top and a y on the bottom, so that now you can use the power rule. So what's the name of what justified this step here?
That's chain rule.
That's right. So one thing you can do if the top and the bottom variables don't match is use the chain rule to change the bottom variable. One thing you can do if the top and bottom variables don't match is use the chain rule to change the bottom variable. Here we changed it from x to y, so then we could use the power rule. The other thing you can do when the top and the bottom variables don't match, which we saw in this example, is to change the top variable. Now we didn't use the chain rule to change the top variable, we just used simple substitution. So those are the two main techniques we've learned when the top and the bottom variables don't match. Maybe you can change the top variable by simple substitution, or maybe you can change the bottom variable, as we changed it here to a y, by using the chain rule. Okay, good. So that's something I think I didn't do a very good job of clarifying last time, but now I think we're seeing that pattern. All right, now.
Yeah, I just had to rewatch the video from yesterday, and it helped a good bit.
Okay, good. Well, now let's try this problem.
Okay. Okay, so product rule. Okay.
Good, good. All right.
I guess I could. Yeah. I guess I could combine these two terms, but okay.
Okay, yeah. Let's see. So the only way we could combine them would be by factoring out an x at this point. And usually that wouldn't be too helpful for the next step of the problem. But that was a good method. Now, that was a good use of parentheses. When do we need parentheses? Usually when there's two different things inside the parentheses to hold them together. So maybe we'll go back and erase the parenthesis on your dy over dx. It's not wrong to put in that parenthesis, but it's an unnecessary complication that might confuse us. Do you see when we're putting in the parentheses and when we don't? We're putting the parentheses, say, around the x squared y to show that the d applies to both of those. But if there's only one thing on top, then it's obvious that the d refers to that. So the parentheses aren't wrong, but they're also not necessary. Okay, good. Okay, so that was a good method for that problem. I'll go back to my screen and review what we just went over here. So how is this problem more difficult than the earlier problems? We can talk about this on my screen now.
Okay.
So how?
Because we're.
Oh, sorry, it was a rhetorical question. I will have the pleasure of answering my own question here. So what I was going to say is this was different, maybe as we're about to say, because in this example we had the same variable on the top and the bottom of the fraction. Of the derivative. That was the easy example. And then in the next two examples, we had two different variables on the top and the bottom. This is the next stage of complication because, as maybe you were about to say, now we have two variables on the top of the derivative. That's the first time we've seen that today. Now we have two variables on the top of the derivative. Well, we're not going to be able to apply any of our simple derivative rules until there's only one variable on the top. So we need some trick to get only one variable on the top. So what was the trick that you used so that you could get derivatives with only one variable on the top?
We use product rule?
That's right, you use the product rule. And can you see how that simplified the top? Before we had x and y on the top of the derivative. But now we have one derivative with only x on the top and another derivative with only y. So that's how that improved it. So what do you do when there's two different variables on the top of the derivative? Try to use one of the rules that you've learned to simplify the derivative so that you have new derivatives with only one variable on the top. And you did that correctly. Okay, good. Now let's try this problem.
Okay. So. Well, I guess I don't need.
Actually, since we now have an expression on the top, this is a case where it probably is a good idea to put in the parentheses. So the one time when it's probably best to leave the parentheses out is when there's just a single variable all by itself on the top of the derivative. Any other time, maybe it's best to put in the parentheses.
Okay. Okay.
Okay, done?
Mm-hmm.
All right. So let's see. This was another case when we had two variables on the top of the derivative, so we had to try to simplify that. So what was your justification for the first line that you wrote?
The first line is we're using the product rule.
That's right. Good.
So derivative of x cubed times y to the fourth plus derivative of y to the fourth with respect to x times. Okay. So. Okay. And
did you erase that plus?
yep.
Okay, it looks like your screen might have frozen here. Let me see if I can fix that. Ah, there it is. Okay. And, okay. Now, notice that you took the dx cubed over dx and you didn't just leave it there, you simplified that using the power rule. But your final answer here still has a pretty complicated expression in it. It has dy to the fourth over dx. That's a fairly complicated expression. We wouldn't want to leave that there if there was any way to get rid of it. So we don't want to oversimplify, but we also want to simplify as much as we can. If we were doing implicit differentiation, we wouldn't be able to solve the problem if we left that dy to the fourth over dx in there. So we're actually not quite done yet with this problem because there's a way to simplify more.
Okay. Okay.
Okay, done?
I believe so.
All right. Now
Yeah.
we made so the line that you wrote down is correct. So let's justify that. What's your justification for the line you just wrote down?
This is chain rule.
That's right. Now, how do we know when we're done? We're done when we've simplified as much as we can, but without trying to simplify something that can't be simplified. Well, we still have some pretty complicated looking derivative there. We don't have dy to the fourth over dx anymore, but we do have dy to the fourth over dy. Now, if there's no way to simplify it, then we'll just have to live with that. But if there is a way to simplify that, then we want to do that.
Okay. I don't think this is really needed. No. And we're good now. We're set up for solving if we're going to.
Okay, yes, that's right. So I think now we're done. Okay, so this problem gave us a little trouble. This would be a good one to go back and try again. So now we've simplified as far as we can. There is no way to simplify the dy over dx, given the information I gave you, but the earlier derivatives we could simplify. And you were right, the parentheses that you erased weren't necessary, although it wouldn't be wrong to leave them in either, if you're not sure. So in your next to last step, you used the chain rule. Why? How did the chain rule help you on this problem? After all, the chain rule, in the line before the chain rule, you only had one derivative. And in the line after the chain rule, you had two derivatives. It seemed like it was a step backwards, not forwards. So how did the chain rule help you?
The chain rule helped because we could get at least one derivative with a like term in the top and bottom. So we could solve for that derivative and then...
Good. Yeah, that's what I was going for. That's right.
Yeah.
That's exactly right. This is something we talked about a few minutes ago at the beginning of the session. The chain rule is helpful for changing the bottom variable on the derivative. The chain rule is helpful to change the bottom variable on the derivative. So in the second line that you have written down on the screen, you had dy to the fourth over dx. Well, there was no way to apply the power rule to that because there were different variables on the top and the bottom. That's why it was a good idea to use the chain rule. The advantage of the chain rule is that now you have the same variable on the top and the bottom of one of the derivatives, dy to the fourth over d to the y. I'm just pointing that out, though, because even though when you first went through this, when you used the chain rule, you didn't then use the power rule. So you had used the chain rule without quite realizing what the advantage of the chain rule was. You used the chain rule, but then you just stopped. But now we can see the whole advantage of the chain rule is that by giving us the same variable on the top and the bottom of the fraction, it set us up to use the power rule in the next step. Otherwise, the chain rule would almost be a step backwards because it introduced two derivatives where there was only one. Okay, so notice in this problem we kept oscillating back and forth between product rule, chain rule, power rule. Okay, so there was some important material here. So generally on these problems, we're going to keep simplifying until we've gotten rid of all the derivatives except for dy over dx. And that's kind of how we'll know when we're done with this type of problem. So I'll go back to my screen. Try writing an expression that this is equal to. How could we rewrite this expression?
Okay. Okay. This is the derivative of f times g. So
Now, since in this problem we started out with the prime notation, let's stick with the prime notation.
Okay. Okay.
Good. What's the justification for what you just wrote down?
This is product rule.
Okay, good. Okay, that's right. That's what I was going for. I'll go back to my screen. I just wanted to go over that to remind you of that because on that last problem we made a mistake with the product rule. Do you remember on the first line of the problem, when you were first doing the problem, you put in a plus in this position as a kind of careless mistake, I think. So I just wanted to reinforce the way the product rule works. It's the derivative of the first function times the second plus the first function times the derivative of the second times the derivative of the second, not plus the derivative of the second. So that was a mistake that we made on that last problem. So so this is just a way. This is the simplest way of summarizing the product rule, so that we can use that reliably. Well, let's try this problem.
Okay, product rule.
Instead of copying that each time, you can just keep writing down an equal symbol
Okay.
to show that each line is equal to the previous line. That'll save us a little time.
Okay, so well. Okay, derivative, chain rule, power rule, derivative. Okay.
Good. That was a good method. Since these are complicated problems, let's write down our justification for each of your steps.
Okay. So here we use product rule. Here we use chain rule slash.
Good. That's right. We use two different rules in that line.
Power rule.
Great. Very good. How did you know it would be a good idea to use the product rule in the first step? How did the product rule help us? After all, we started with only one derivative, and after the product rule, we had two derivatives, so it might have seemed like it was a step backwards. How were the two derivatives that we got from the product rule superior to the one derivative we started with?
Because they had the same, well, the one on the left had, well, actually, sorry, reword that. They both had the same variable on the top and the bottom once rewritten.
I don't think that's quite true, because one of them was dy cubed over dx. That's not, so that one doesn't have the same variable on the top and the bottom.
Okay.
So we haven't quite put our finger on it yet. So the derivative we started with was d of y cubed x to the fifth over dx. That, and then we ended up with two new derivatives, dy cubed over dx and dx to the fifth over dx. Even though we got two derivatives, they were both better for us, easier to work with than the one we started with. What was the, how were those two new derivatives simpler or better than the one we started with? How were they easier to work with? What was the advantage of using the product rule?
Because you have one term in each, and also you can use the power rule for one of them sometime. Well, if it ends up like that, you can use the...
It's true that afterwards we could use the power rule, but we haven't quite explained why. So the advantage was, the thing that was really messing us up with the original derivative is not just were there different variables on the top and the bottom of the derivative expression. The problem was that there were two variables on the top, right? Mm-hmm. On the top there was a y and an x. Well, there was nothing we could do with that until we simplified it so that each derivative only had one variable on the top. So notice when we started with dy cubed x to the fifth over dx, that was very difficult to work with because there was two different variables on the top. I'll go back to my screen. This has two variables on the top, both the y cubed and the x to the fifth. But once we've used the power rule, now this derivative has only one variable on the top. It's still not the same variable as the one on the bottom, but it's still progress because there's only one variable on the top now. And the other derivative also now has only one variable on the top. So the product rule here was helpful to us because it went from a situation where there was two variables on the top of the derivative to derivatives where there's only one variable on the top of this derivative and only one variable on the top of this derivative. So if there's two different variables on the top of a derivative expression, we generally have to use some trick to get new derivatives where there's only one variable on the top of the derivative expression. Okay? Now let's try this problem. Okay.
Oh. Natural log of y. That was over d. Okay, so we have product rule here. And Natural log of 4 is...
What was the original problem? Read that aloud.
The derivative of x squared times the natural log of y.
Okay, so it looks like you. I didn't know whether you misread my handwriting or not, but maybe you read it correctly, but you just got confused by your notation.
Yeah. Okay. Y is just... Wait. That's not true. This is... Okay, so... One second, I'm sorry. Derivative. Product rule.
Good.
Chain rule. And then this is just definition. Okay.
Okay, good. Okay, that's a good way to set that out. Now, you had a little trouble figuring out how to justify your last line. Since that was so straightforward, maybe we don't need a justification for it. Technically, the formula that you used is not a definition, but a theorem. There's a theorem that proves that that's the derivative of the natural log. So we could say that you used just the rule for the derivative of the natural log, or maybe that one was straightforward enough that we don't need to write down a justification for it. We never really gave a name to that rule. Okay. The important thing that you did here is that you realized that you weren't ready to take the derivative until you'd used the chain rule. Notice how it was, I think you were just about to already have written that the derivative was just 1 over y, but then you caught yourself and realized you needed the chain rule first. So that's important. Okay, so why did you use the product rule in the first step? What was the advantage of using the product rule? How are the two derivatives that we got from the product rule superior to the one derivative we started with?
Because we started with 2 and we want to try and break that up and have a single variable for each derivative, and that's what we did.
Okay, sounds like you're on the right track. You said we started with 2. We started with 2 what?
With 2 variables.
Where?
Right here.
On the top. That's right. The problem is that there was 2 variables on the top of the derivative, and after the product rule, we only had 1 variable on the top of each derivative. Okay, very good. And then what was the advantage of using the chain rule when you're ready? Take your time.
Okay, when we used chain rule,
How did that? How was the derivative that we got after the chain rule superior to the one we started with?
okay.
So you started with d, natural log of y over dx. And then after you used the chain rule, you had d natural log of y over dy. How is that second derivative better than the first one?
It's because we have the same variable on the top and bottom on the left term, so we can use product rule at that point.
So then we can use the rule for natural log. Yeah,
right.
Okay, that's right. D, natural log of y over dx, is tough to work with because there's two different variables in the top and the bottom. But then after we use the chain rule, we change that into d natural log of y over dy. And once we did that, then we were in shape to use the rule for the derivative of a natural log. We also introduced a new dy over dx term, but that was an unavoidable cost. And it doesn't bother us too much because we know we need that expression for implicit differentiation anyway. Okay, so the reason I'm asking you to justify those steps is so that we can be flexible and adapt to new problems, because each problem is going to be different. We can't just assume that we always start with the product rule. We have to know why we did the product rule and then the chain rule here. So if we see a different problem, we might adapt to that. Okay? All right, so we ended up with the correct answer for that problem. So I'll go back to my screen. Here's another problem. Let's try this one.
Okay. So we need to use chain rule right away. Sign the Okay, so this would be I want to put u here, but I don't.
Okay,
like
yeah.
that.
I guess this, so you're right. We need to start with the chain rule here. That was a good idea. I suppose we've never quite done the chain rule in exactly this situation before, so we'll have to work out what's a good notation for it. But you're right. So think back to how we do the chain rule. Remember that we do the chain rule by doing the derivative of the outside function. And we remember that we invent a new variable we generally invent a new variable for the outside function. So yeah, u would be a good variable here.
Okay.
Now let's be careful with that. So we take the derivative of the outside function with respect to what?
With respect to u.
That's right. That's something we didn't make a big deal of before. But if you go back in your notes and look at the three-step process we originally wrote down for the chain rule, we said that you have to rewrite the outside function as a function of... So step one was rewrite the outside function as a function of u. Then step two, take the derivative of the outside function with respect to u. And then continue. Okay, so that was a good step.
Now we use product rule. So cosine of x squared times 2x so we use product rule here. And then one more. Oh, no. Okay.
Okay, so I think this was a harder problem than the ones we did before, but you had the right idea here. So what's the justification for the first line that you wrote down in your solution?
This first line is chain rule.
So let's make a note of that. And let's do the same for the next line.
And then, okay, well, yeah, oops. This was product rule, and this is the power rule.
Right. Okay. Okay, I didn't realize this going in, but yeah, so it looks like we now have kind of two different types of situations where we use the chain rule, and so we have two different notations. Remember that when we originally learned about the chain rule, we were always in the habit of inventing this new variable u. But actually, recently, when we've been using the chain rule, we've had situations where we didn't need to invent that variable u. But as you had the right idea in this case, this was a case where we needed that variable u again. So you had the right idea there. But then remember, remember the chain rule is step one, rewrite the outside function as a function of u. Then step two, take the derivative of the outside function with respect to what?
Of the outside function?
Yeah, when we take the derivative, so we start by rewriting the outside function as a function of u, and then when we take the derivative of the outside function, we're going to take the derivative with respect to what?
To u.
That's right. Remember, that was the thing that was the one part you weren't getting right originally. At first, you had d sine u over dx, but that doesn't really match the chain rule. We had to change it to d sine u over du. And then we continued to take the derivative of the inside function with respect to x. We took the derivative of the outside function with respect to u, and then just as we've always done in the past, we took the derivative of the inside function with respect to x. Okay, so how was this problem different from the one we did before? Why was this a little trickier? After all, the last problem we did, we also used the product rule and the chain rule. Well, the difference is, if you remember on the previous problem, first we had to use the product rule, and then we used the chain rule. I think we have it written down, yeah. In the previous problem, first we used the product rule, and then we had to use the chain rule. But on this problem, first we had to use the chain rule, and then we used the product rule. So that's what I meant when I said you have to be flexible. You can't assume that every problem is going to be the same rules in the same order. You have to use your own judgment to decide which is the one that you have to use first. And you did figure that out. You saw that you were going to have to do the chain rule first here. So that's good. So we have to adapt to the different types of problems that we're seeing. Okay, so we've also seen that now, say going back to this example here, here was an example where we used the chain rule. So here's an example where we'd use the chain rule. Now, in this example, we didn't have to invent a new variable. In this example, we didn't have to invent a new variable u. We were able to use the chain rule just by sticking with our y and our x. But in the example we just did, we did have to invent a new variable. So I probably should be able to give you a rule or a reason that tells you when you need to invent that u and when you don't. But I haven't thought about that yet, so I don't know what the rule is. So we'll just have to use our judgment. So we've seen sometimes when we do the chain rule, we have to invent a new variable u. Other times, like this example, we didn't have to invent a new variable. So we just have to keep in mind that there's two different types of situations now that we've seen where we're using the chain rule. Okay.
And I think maybe perhaps we could use the same notation, but with just different variables. Instead of using u, we could have just rewrote it as d of p. I don't know.
Let's see. On the problem we just did?
Mm-hmm.
Okay, I'm not sure if I quite followed what you were saying there. It's true that you don't have to use the variable u. You could use any made-up variable. We're just using u because that's what we've used in the past. Now, that wouldn't be d of p. The key thing is there wouldn't be a p on the top. It would be p on the bottom. Or, there would be d sine p. So if you wanted to, you could invent the variable p instead of u. But we may as well stick to the variable that we've been using in the past, which was u. Okay, hopefully as we do some more examples, we'll just get a feel for those. All right. Okay, let's try this example. That's not a complete example, is it? So I meant to write this. Let's do this.
Okay. Oh. Okay. So, product rule. Respect to x. Well, this is with respect to. Says okay.
Okay. Let's write down our justification for the first line of your solution.
Okay, the first line. Use chain rule.
Good. Now, you didn't quite use the correct notation for that line with the chain rule.
Okay. Yeah, this part I was getting a little tripped up on. Okay. So derivative of cosine u with respect to well, is this just u? Would do. Huh. This is the same.
So that term actually was correct. It was the inside term that we didn't write down correctly.
Ah.
Okay, yeah. So how would we read that dxy over dx? How do we read that aloud?
That's the derivative of xy with respect to x.
Good. So what does the d on the top stand for?
That's derivative.
Derivative of. And what does the d on the bottom kind of stand for?
With respect to.
That's right. So we need to include both of them.
Okay.
We need to include both of them, or the derivative doesn't make any sense. We always need to include both of those. Now, you proceeded with the rest of the problem as if you had included both of those, but it's important to get the notation right. Okay, and then you didn't seem like you had very high confidence for the outside portion, but you actually did the outside portion correctly. So remember, the process is, for using the chain rule, step 1, rewrite the outside function as a function of u. Well, you did that because you wrote it as cosine u. Then step 2, take the derivative of the outside function with respect to what?
U.
And then you did that. You did d cosine u over du. So that part was correct. And then step 3, what do we plug in for u?
The inside function.
And you did that correctly too. So you seemed a little uncertain about the outside function portion, but you did that portion correctly. Okay, so what was your justification for the next line of your solution?
Okay, for the next one we used
Then we use the product rule. Okay, good. So you did this problem correctly, and then the last line you used a form of the power rule. Dx over dx is a version of the power rule. Okay, good. So we ended up getting this correct. We weren't 100% confident, but you ended up doing that correctly. I'll go back to my screen. All right, so now I'm going to give you a trick question.
Okay.
Here's a trick question. How would you read this aloud?
The derivative of y divided by x.
Okay, it was a trick question because what we should have said is this is meaningless.
Okay.
When we use the d derivative notation, there's got to be a d both on the top and the bottom. When we use the d, that notation, there has to be a d both on the top and the bottom. We can't just have one d without the other. This is a little confusing because maybe later in your course you will start to use d's all by themselves, but we haven't done that yet. So far, a d by itself is meaningless. We have to have two d's or it doesn't mean anything. So how would you read this aloud?
That's meaningless.
Yeah, trick question. So if you saw this, you would say, gee, I messed up. Somehow I messed up my notation. I shouldn't have written that down. How would you read this aloud?
That is also meaningless.
Yeah. So what would it mean if you saw this written down? It would mean you made a mistake and you have to go back and fix it. So there always has to be two d's, a d on the top and the d on the bottom. I'm just mentioning this now because I've seen we've made that mistake a couple of times in our work. We have to make sure to have a d both on the top and on the bottom. Otherwise, our symbols are meaningless so far. Okay, good. Now let's try this problem.
Derivative of tangent is no. Okay. Well, okay. So up here we use chain rule. Now for our chain rule, reduce product rule. And then power rule. Okay.
Okay, done?
Yep.
All right. What was the question?
The question was asking us to find the derivative the derivative of tangent of x squared y cubed with respect to x.
Okay. Good. All right. So there was a mistake in the first line that you wrote down that you've labeled chain rule. See if you can find the mistake that you wrote in the first line of your solution.
Tangent u with respect to du. Okay.
Oh, did you leave out that D?
I did.
I didn't even notice that. Okay, yeah, so there were two mistakes in that line. All right, so one was we can't leave out that D. Remember the exercise we were just doing a couple minutes ago about how you need to have a D both on the top and the bottom or it's meaningless. Okay, so the mistake I was going for was that the 3 changed into a 5 there. All right, well, that was just a careless mistake. Let's save time. Instead of redoing the whole problem, let's just pretend that it was y to the 5th from the start. That way we don't have to change everything in the problem. So why don't you change the original question to x squared y to the 5th? Because that was just a careless mistake on your part. You did the problem correctly after that. Okay, so if it was y to the 5th, then the rest of the problem is correct. Okay, I didn't even notice that missing D, but that's important too. All right, it was good that you went back afterwards and wrote down the justification for each line, but even better would be to write down the justification as you go, because the purpose of writing down the justification is to help us keep our bearings and avoid mistakes, and it'll do that better if you're writing down those justifications as you go. Okay. Let's see. So at first you used the chain rule, and this was the situation where you had to introduce a u. Then the next line, did you really use the product rule in the next line?
Yeah, we did.
Yeah, you did. Okay. And then in the next line, did you really use the power rule? Yeah, you did use the power rule. You said dx squared over dx is 2x. But there was another rule that you used that was maybe more important in that line.
We also used chain rule.
And that was the more important one. That's the one that's especially helpful to write down. By the way, there was another notational mistake in that line, the one that we have labeled as power rule, chain rule. How could we improve our notation for that line? Oh, did you leave out a D? I didn't even notice that. All right, there were two mistakes. All right, we really have to watch out for that mistake. Okay, there was another notational mistake in that line as well. Can you see the other problem with that line?
I did. Yes. Hopefully that was 2x. That's good. That's good. Well. Okay, I think that's okay. All right, yep.
That's what I was actually going for, the parentheses. So it was good that you saw to put the parentheses in when you used the product rule. That was good. Then they disappeared. Fortunately, they came back in the final answer. If they hadn't come back, the answer would have been wrong. But we should keep those in each line. One thing that's challenging in the course is that we need to know when to put in parentheses. Now, I'm not sure, you added a 5. Why did you add that 5 to one of the terms?
Okay, that was, yeah. I don't know. I was just looking for something to fix.
I know sometimes when people look, if I tell someone there's a mistake, sometimes they'll fix something that ain't broken. All right. So, well, how can you tell? Does that Y need a 5 or not?
It does not, because we have it over here. I mean, I'm not sure how to justify that, but...
So the key thing is, what are we treating as our outside function now? Yeah, so the point is the whole purpose of using the chain rule here is to simplify. The outside function is now the y to the 5th, and the inside... well, the point is, remember that when we use this notation for the chain rule, the easiest way to see it is, remember that when we use this notation for the chain rule, the term on the bottom of the first derivative should match the term on the top of the next derivative. Okay. All right, so let's see. And then what was your justification for the last line?
This was power rule.
Again.
Yeah.
So notice this problem was one step harder or more complicated than any of the problems we've done to this point. because you did the chain rule, then you did the product rule, then you had to do the chain rule all over again. So this is the first problem, I think, where we've had to do the chain rule twice, and then the power rule again. So this was one more layer of complication and difficulty. But I think you understood it in this case. There was a couple of careless mistakes here, but you understood the basic conceptual approach, even though this was a little bit more complicated. It's still the same basic idea. Okay, so I'll go back to my screen. And let me just remind you of the notation for the chain rule. So the key point is, when we're doing the chain rule, these two terms should always be the same. When you're doing the chain rule, these two terms should be the same. Is that how we've been? Actually, maybe I shouldn't say that. We've actually done some examples where they're not exactly the same. I guess it's a little bit tricky. We haven't been 100% consistent. Okay, I think you get the idea, so I'm not going to try to put it into words because I'm messing that up. All right, so let's just go on to another problem. So let's see. Next problem is this one. Okay, let's try this.
Okay. Okay, so dx Okay, so we have 3x squared plus, here, let's write this in. This is really, product rule, derivative of x times y, derivative of y times x, plus Okay, so okay. So these two terms are coupled. So we gotta. Factor this. X plus okay. So we just rewrote. Power okay.
Okay, wow, that was a lot harder than I thought. It was. There's a lot to these problems. I didn't realize there could be so much packed in one of these. Okay, that was a big jump up in difficulty from what we were just practicing a minute ago. But I think we cleared that hurdle. I don't. You made a couple mistakes, but I think you caught all of them as you were going. That's the important thing. Everybody makes mistakes on a long problem like this. The important thing is that you took your time and you caught the mistakes. So that's pretty tough,
Right.
but I think we made it through it. Okay, so let's see. Let's look at this one more time. Let's scroll to the top of the problem. So what was the name of the method we used for solving this problem?
Implicit and differentiation. I'm not sure how to pronounce that word. Implicit.
Differentiation. Remember that calculus is the study of derivatives.
Okay.
So here when you take a derivative, that's called differentiation. Here we're doing what's called implicit differentiation because we didn't solve for dy dx directly, but instead it kind of emerged in the course of the problem. Okay, so this is so all of the problems that we've done earlier today were kind of warm up for this. I guess I realized after our last session that there was a lot more involved in this than that had been apparent to me at first. So we needed to do a little bit more warm up, and now we're ready to dive in. And you applied everything we've been practicing today, so that's good. Let's see. It looks like one thing is it's good that you went back and said what your justification for each line was. But again, it'll probably be more useful to you if you write those justifications as you're doing the problem. Okay, so I noticed that the first line you wrote, you just said rewrote. What is it that you rewrote?
We rewrote the derivative in this form. So we took the derivative of both sides.
Okay, now the second thing you said is correct, but that's more than just rewriting. You didn't actually just rewrite the previous expressions. What you did was you took the derivative of. So did you just rewrite the equation? No. Instead, you took the derivative of both sides of the equation. And did you just rewrite dy over dx? Well, no. What you have written down there is not the same as dy over dx. So rewrite is not quite the right thing to say here. There's not really a name for what we did there. If you want to, so not every line necessarily needs a justification. The ones that I think are especially important to justify are when you're using our calculus rules, like the sum rule, power, product, and chain rule. But if you had to write down a justification, you could say, took the derivative of both sides of the equation. What you did there is you took the derivative of both sides of the equation. Remember that we know as a basic principle of mathematics that it's perfectly legal to take the derivative of the left-hand side of the equation as long as we also take the derivative of the right-hand side of the equation. We can do anything we want to the left side of the equation as long as we also do the same thing to the right side of the equation. That's the golden rule of math that we learn in high school. Okay, but the key steps that need to be justified, I think, for us are the calculus steps: sum rule, power, product, and chain rule. And you can see how complicated this was. You used the sum rule, then you had another line where you used the power, product, and chain rule all in one line, and then the power rule again, and then we had some algebra at the end. Okay, so let's see. We used the sum rule, then you used power, product, and chain rule, then you used the power rule again, then you did some algebra. I noticed that, I noticed that when you use, well, I guess I'll come back to that, but use the power rule. At first, when then you had to move the 3x squared to the right-hand side. I noticed at first when you wrote the 3x squared on the right-hand side, you wrote it as 3x squared, but then you caught that mistake and wrote it as negative 3x squared. That's good. What do we do to move the 3x squared from the left side to the right side? What's our justification for moving it from left? What do you have to do to the equation to move the 3x squared from the left to the right?
We add a negative 3x squared to both sides.
That's right. And if you remember that's what you're doing, that makes it plain that you're not actually moving it, you're changing it. It changes to a negative 3x squared when it gets to the right-hand side of the equation. So you caught that mistake. Okay, I'll go back to my screen. So that shows some good progress. That's a pretty hard problem, and you had to put together a lot of the different things we've talked about, and we did that. So going back to here, I just wanted to remind you of the product rule. How would I write the product rule here? What does this come out to be?
This is f prime times g plus g prime times f.
I just wanted to remind you that you have a tendency to do this. So you caught that mistake here again, but we just should call our attention to that so we can start avoiding that. Oftentimes when you're doing the product rule, you put in a incorrect plus sign. So we just need to watch out for that. It's not f prime times g. It's not f prime plus g. It's f prime times g. And you caught that mistake too. So the important thing is to catch the mistakes. But it's just good to call our attention to that so that we can start avoiding that. I'm sorry, you were going to say something?
Oh, I think it's because I was using parentheses before when I was doing them, like for the mastery test. So maybe I should go back to doing that. Like, I guess even though they're not needed, it kind of reminds me to.
Okay. Sure.
Yeah.
Okay. Yeah. If you think that helps, that's fine. Fair enough. Okay. All right. So I'll write down the problem on my screen. try this problem.
Okay. So, product rule. Okay. Okay, so on the left-hand side we have product rule, derivative of y times cosine of x plus derivative of cosine of x times y. And we can rewrite this as summable derivative of x cubed with respect to x plus derivative of the fourth. Okay. So this is good. Okay, so we could just divide. Well, since we have dy over dx on both sides, can we leave one of the terms on one side and solve for just one of them? Unless I did this wrong. 4y cubed.
Okay, no, I think your work so far is correct.
Okay, so I guess I could. Oh. Okay.
Okay. All right, so we did the calculus portion of this problem correctly, but as oftentimes happens in calculus, we got tripped up by the algebra. Unfortunately, a lot of people don't remember their high school algebra too clearly. And also, even if they know the high school algebra, it might be hard to apply it with these types of symbols. So we do have some algebra problems here. So first of all, our goal here is to solve for dy dx, right? We need to figure out what dy dx is. So what you've said here is that you can figure out dy dx by plugging dy dx into the left side of the equation. But notice that gives you a kind of chicken and egg problem. The whole point here is we don't know what dy over dx is. So it's useless to say that we can plug dy d over dx into the left-hand side to figure it out on the right-hand side. When you're solving an equation for a variable, you need to get that variable by itself in the equation, and it needs to be the only variable in that equation. All right. Also, that last step wasn't actually correct algebraically. If you divide the right-hand side by 3x squared 4y cubed, they wouldn't actually cancel because they're playing different roles there. But let's go back to my screen for a moment and talk about the algebra that we need here. Do you know how to solve this equation?
Yep. We can. We can add a negative 4x to both sides. So.
Okay, let's try that on your screen.
Okay. Negative 8 plus 2. Okay.
Let's see. So let's make sure. So what did you do? What was the first thing you did?
Subtracted negative 4x from both sides.
That's right. That's legal. So that gave you negative 2x on the left-hand side. And then what was the next thing you did?
Negative 8 to both sides.
Okay, good. All right, so that seems right. So the point here is, I'll go back to my screen now for a moment. would you agree that this would not be considered an acceptable answer? Even though I haven't made any algebra mistakes. So there's no algebra mistakes here. I subtracted 8 from both sides. Then I divided both sides by 2. So there's no algebra mistakes here. But this is, do you see why this is not an acceptable answer?
Because we have x on both sides.
Yeah, I haven't actually solved for x. You have to get x all by itself on one side, or you haven't solved for x. So that would not be acceptable. I'll erase that since that was correct algebraically, but it didn't actually take us to the answer. So notice, what do you do if you have a variable on the left and a variable on the right that you're trying to solve for? Well, what you do then is you try to move one of those terms to the other side so that the variable only occurs once. You try to move one of those variables to the other side so that it only occurs once. Also, going back to here, would you agree that, let's see, what am I trying to do here? Notice you can't just divide both sides by 3 plus 4 here. This is incorrect algebra. This is kind of something that we tried to do on that last problem. You can't just divide by 3 plus 4 here. This doesn't cancel because the 4 here is multiplied times the x and the 3 is not. That would be an incorrect algebra step. All right, well, you knew how to solve, oh, did I erase the whole thing? Rats, I didn't mean to do that. Well, you knew how to solve that previous example. What was the previous example? Let me write it down here again.
2x plus 8 equals 3 plus 4x.
You knew how to solve this example. But here I had only one variable and then a bunch of numbers. Here's where people maybe start to lose their intuition when there's tons of variables. Do you know how to solve this equation for z? Give that a shot.
Okay. Let's see. Okay. So we need to solve for z. Well,
I'll give you a hint. This problem is identical to the one I just gave you. So you might want to compare this to the previous example. Do you see why I'm saying they're the same exact problem? The one about the 2x plus 8 equals 3 plus 4x. They're the same exact problem, you just have less intuition for it because there's more variables and fewer numbers. But we should use the same exact method to solve this problem as we did when there were some numbers in the mix. Do you see why I would say they're the same problem?
because we have a z on both sides.
Okay, yeah. So that's part of it. So our basic challenge here is that the z is on both sides, but also they just look exactly identical to each other. It's just I've replaced the numbers with variables.
Right.
So if we knew how to solve the previous example, we should be able to apply the same methods here.
I guess
because the letters stand for numbers.
Right. Okay.
So think about what your steps were for the previous example, and we can apply the same steps here.
Well, I think we stopped here. Well, no, we solved. Okay. Oh.
Okay, that would work, but let's be a little more careful. Let's erase that last part that you wrote down, even though technically that's right, but let's not skip any steps. So let's erase the divided by a minus q on the left-hand side as well. Okay, so what are we trying to do here? We're trying to get z. We're trying to get z all by itself, and we're trying to get there to be only one z, right? We want all the z's in one place, only one z in the problem. So we've made some progress because there used to be a z on the left and a z on the right, and now both z's are on the left. But the next thing we have to do is rewrite the problem so there's only one z. This is something we've actually already worked on previously in some previous examples, but you might not recognize that we have to apply it here. The method we've used when we had this situation before was factoring.
Okay. So
Now is the better time to divide by a minus q, because now we have a better justification for it.
okay. Cool.
Okay. Okay, so I said this was a review of high school algebra, but I guess the problem wasn't so much that we didn't know the algebra. You knew how to do the problem when there were numbers in there, but people lose their intuition when there's fewer numbers and more variables. But we ended up using the same techniques here as we kind of did before. So remember, when you're solving for something, you need to get only one version of it all by itself. So at first there was a z both on the left and on the right. So how did you get your second line here? How did you go from the first to the second line? What did you do?
From the first to second line, we added a. Well, we subtracted QZ from both sides.
That's right. Why did you do that? What was the advantage? The advantage was then all the z's were on the same side of the equation. The first step was to get all the z's on the same side of the equation. Good. And now we want to try to get the z's by themselves. So how did you go from the second line to the third line? When you're ready.
We subtracted a d from both sides.
And why did you do that? Because you're trying to get the z's by themselves. Good. And then the next line was the one that really gave us some difficulty. We still had two z's on the left-hand side. How could we reduce that to only one z? By factoring. That's a technique I think we've used on some previous examples, but sometimes it can be hard to see when we can do that. Okay, so I'll go back to my screen. So here's the previous example that we did. Do you see how I got each of these two steps?
Mm-hmm.
Now, notice we could factor here too. What would go in the parentheses?
2 minus 4.
And then you would get this. So notice you could do this by factoring too, but basically this is so easy for us, we kind of do this step in our head. We just say, oh, 2x minus 4x is negative 2x. But why is 2x minus 4x negative 2x? It's because of this factoring argument. So this makes clear how this example was more similar to this example. Okay. Try this problem. Oh, Sorry. All right, try this problem.
Okay, I'm going to solve for q. Well, I already have q on the same side. So I'm just going to reorientate this problem. Okay. Can try to solve for q, so we can factor out q. Y plus h equals q equals w plus hy minus j over y plus h. So we q on the same side, we rewrote the problem, and then we subtracted j, and then we factored q out, then divided by y plus h. Okay.
Okay, good. All right, so we did that correctly. So in this problem, this was just to reinforce and review this factoring technique. If you're solving for a variable, first you have to get all of the copies of that variable on the same side of the equation. Well, we already had that from the start here. And then if you have multiple copies of the variable on the same side of the equation, we can use the factoring technique to rewrite it with only one version of that variable there. Okay, well, if you remember, this was all a big digression. We were actually in the middle of a implicit differentiation problem, but we got stuck on the algebra. So now that we've gone off and done the algebra, let's see if we can find that old problem that we quit in the middle of, and see if we can figure out our algebra here. So you should probably erase the last line that you have written down there, and try to come up with some different algebra to proceed with the problem.
Okay. All right. So try to find dy over dx.
Good. That's good that you asked yourself that question. You can't even start unless you know what you're trying to solve for. So that's an important step.
Yes, we need to get dy over dx on the same side. Well, I suppose we could factor this. I guess that doesn't matter. Okay. So we added this, or subtracted this, and we subtracted a negative sine x times y. Okay. So now we can factor.
Well, you may have noticed that the student had made a couple algebra mistakes in going from this line to this line. And I feel that I didn't do a very good job during the session of explaining the algebra here. So instead, I thought I would just go back and re-record this small part of the lesson to try to explain the algebra that's involved here a little bit more clearly than I managed to do during the tutoring session. Again, if you haven't noticed already, you might want to pause the video now and try to find what are the algebra mistakes that the student made going from this line to this line. So this line is correct. This line is correct, but this line has some algebra mistakes. You might want to pause the video and see if you can find those. Well, now I'll go over and talk about the key algebra ideas that are involved there. So suppose we're considering this multiplication. Would you agree that this is the same thing as this? I hope you would agree that these are both the same thing. And would you agree that both of these are the same as this? I hope you'd agree that all three of these are the same, because after all, they're all equal to negative 15. Negative 3 times 5 is negative 15. 3 times negative 5 is negative 15. And 3 times 5 is 15, and then if you put a negative in front of it, that's negative 15. So now to look at that more algebraically, would you agree that this is the same as this? I hope you would agree these are both the same, and that that is the same as this. It's just the same pattern as we saw up above. In fact, all of those would be easiest to write like this. There's really not too much need to put in all these parentheses here. We could just write all of them more simply like this. Okay, so here's the key to the algebra issue here. It's important to see how we can move the negative sign around here. The important thing is that the negative sign is clearer maybe in this position or this position than this position or this position. So let's say we had and let's say our goal is to solve for x. Suppose we're trying to solve this for x. You might want to pause now and see if you could solve this for x. Well, we have to get the x by itself, which means that we have to move this term to the right-hand side. We need to move this term to the right-hand side. But I think it would be easy for people to get confused and make mistakes here because of this negative sign. So there's a bunch of ways you could deal with this, but here's what I think is the simplest thing to do. The simplest thing to do is to rewrite this like this. That is, we can, instead of saying that we are adding a negative z, we can just say we're subtracting z. Just like here, instead of having a negative x, we could take the negative outside of the parenthesis. And I think that makes it easier to move this term to the other side. Now I think it's clear that what we need to do is add zw to both sides, because the way to undo subtraction is addition. Okay, and now it should be easy to solve for x by dividing both sides by y. So the key point I wanted to make here is that when you're doing algebra, instead of having this addition of a negative number, you might find it easier to think through the steps if you change adding a negative into subtracting. That was the key. Instead of adding a negative, you might find it easier to call this subtracting. Now, of course, if this algebra is easy for you anyway, then you can just ignore all of this. If this is easy algebra for you, then you can do it any way you like. But if you're having trouble with this algebra, I think this is the clearest and most straightforward approach to dealing with this type of negative sign. So the trick is turn the negative sign into a subtraction sign. Now, the important thing to notice here, notice that we moved this negative zw term to the right-hand side. When we did that, did the w turn into a negative w? No. If you recall, that's the mistake that the student had made. The student had thought that when you move this kind of term to the right-hand side, they have to change the sign on the z and the w. So they changed the z, the negative z to z, but they also changed the w to negative w, so to speak, in terms of the problem they were working on. But when you attack the algebra this way, you can see that's not correct. The w does not become a negative w here. I hope that algebra is clear. Okay, so that's some tricks that you can use to deal with situations when you have negative signs. You can turn the negative signs into subtraction signs. By the way, we don't really need all of these parentheses here. I'm just putting in the parentheses because the student had a lot of parentheses in their own algebra. But it would be perfectly okay to get rid of a lot of those parentheses. They're not really adding anything. And that gives us the same thing here. So you could just as well rewrite it like this, and we would get the same answer. Okay, so now let's go back and try to solve this problem correctly. Well, this was the incorrect approach. So now let's move down and try to do a correct approach. You might want to pause the video now again and try to solve this correctly using the algebra skills we were just talking about. Okay, so now we're going to apply that algebra and try to continue the algebra here. Remember, this was the incorrect approach up here. Incorrect. Remember, our goal is to solve for dy over dx. If you haven't done so, maybe now you can try again to solve this algebraically. Pause the video. Okay, so what's our first job here? Well, in order to solve for dy over dx, the first thing we have to do is get all the dy over dx's on the same side of the equation. Before we do anything else, we should get all the dy over dx's on the same side of the equation. That means we either have to move this term to the left-hand side, or we have to move this term to the right-hand side. So I'm going to move this term to the left-hand side. This term is being added to the right, so we can undo that by subtracting. So I subtracted that from both sides. So now the left-hand side Now the left-hand side has this new term, negative 4y cubed over dy times dy dx. And the 4y cubed dy over dx term has disappeared from the right-hand side. Do you see why this is progress? This is progress because now all the dy over dx's are on the same side of the equation. And dy over dx is what we're trying to solve for. So what's our next job? By the way, notice that when we did this, well, all right, hopefully that's clear. So let's continue. Now what's our next job? Well, we need to get the dy over dx by itself on the left-hand side. We need to get the dy over dx by itself on the left-hand side. So we need to start moving other stuff on the left to the right. We need to start moving all the other junk on the left to the right-hand side. But it's important to do this in the right order. Which term can we now move to the right-hand side? Well, the term now that's easiest to move to the right-hand side is this term. Now is the time to move this term to the right-hand side. And this is where the student had gotten confused. And here's where the algebra we were talking about could be helpful. Some people might find it confusing to try to figure out how to move this term because there's a negative sign. Well, remember the trick we went over. We can turn that negative sign into a subtraction sign, because I think most people have better intuition for how to deal with that. So here we're using the algebra trick I was mentioning earlier. We turned the negative sign into a subtraction sign, and the advantage of that is now it should be obvious how to move this term to the right-hand side. It's being subtracted, and the way to undo subtraction is addition. So the negative sine x plus y disappears from the left-hand side. And on the right-hand side, we have 3x squared, and now the new term, plus sine x times y. So now we've successfully moved that term. Maybe it would be good to go back and see what the student's mistake was when they did that. Notice that when the student tried to move this term to the right-hand side, they changed the y into a negative y. They changed the y into a negative y, but notice when we do it correctly, that's not how it turns out. This should be plus sine x times positive y, not sine x times negative y. Okay. So again, I'm not saying this is the only way you can do this algebraically. If this algebra is easy for you, then you can do it whatever way is comfortable for you. But if this is algebra that gives you trouble, then the method that I just demonstrated is, I think, the best method. Turn the negative sign into a subtraction, and then it should be clear how to move the term to the other side. Okay, so that's how to fix the algebra mistake that the student had made. Hopefully it's clear now how the student made a mistake going from here to here. Let me also say something about the order that we're doing these things in. Maybe I could call this over here the first thing that we did, and this over here the second thing. I think it's important, if your algebra is weak, to do things in the correct order. It didn't make sense to move the sine xy to the right-hand side until this point in the problem. It would not have been a great idea to move the sine xy to the right-hand side at this point. That would probably confuse us. Do you see how it's not helpful to move the sine xy to the right side here? How would that not help us? Well, moving the sine xy here was helpful because it helped us to isolate the dy over dx. Remember, we're trying to get the dy over dx by itself. Well, by moving the sine x to the other side, sine xy to the other side, that put less stuff on the dy over dx side. But at this point, we weren't ready for that yet because there was a dy over dx on both sides. What's the point in moving this term to the right? So we might say, gee, I have to move this to the right to get it away from this dy over dx. But that would just move it closer to this dy over dx. So this point here is not a good point in the problem to move this term. It's confusing and not too helpful to move this term at this point. because it would just be moving from one side with the dy over dx to another side with the dy over dx. Instead, first, we get all the dy over dx's on the same side of the equation. And then it makes sense to move this term to the right-hand side, because now we're accomplishing a clear goal by doing that. Now we're accomplishing the goal of getting the dy over dx's by themselves on the left-hand side. That's something else the student did in their work that I think was confusing them. They were maybe moving this term too soon. They were moving this term before they had moved this term, or at the same time that they were moving this term, and they ended up confusing themselves a little. So it's better to put these in this order. Now again, everything I'm saying here again is only for students who feel their algebra is somewhat weak. If your algebra skills are strong and these problems are easy for you, then again, you can do them whichever way feels comfortable. But if you find yourself making algebra mistakes in these problems, then that's the advice I would give. Do only one thing at a time. First, move all the dy over dx's to the same side of the equation. Only then should we do things like moving this term to the right-hand side. Okay, now the next step is, remember that we have to continue getting dy over dx by itself. Now we have two different dy over dx terms on the left-hand side of the equation. What we want is a single dy over dx term. Right now we have two dy over dx terms on the left side of the equation. What we want to solve the equation is to have a single dy over dx term. What's the method that we can use to go from two dy over dx terms to only one dy over dx term? I think we've already seen that earlier in the videos. It's factoring. When you factor dy over dx out of this term, what's left is cosine x. And when you factor dy over dx out of this term, what's left is 4y cubed. Okay, good. And notice here now we accomplished our goal of moving from having two dy over dx's to only one dy over dx. Remember, we're trying to solve for dy over dx, so we have to get the equation to the point where there's only one copy of dy over dx, so this was progress. Now again, let me mention that it's best to do these steps in this order. I guess I could call this our third step here. For example, this point here would not have been a good time to factor. This would not have been a good time to factor dy over dx. Why is this probably not a good time to factor dy over dx? Because one of the terms doesn't have a dy over dx in it, so you could easily get confused if you tried to factor here. So this is not a good point to factor the dy over dx, because there's still a term on the left-hand side that doesn't have the dy over dx. Instead, first we move this term to the right-hand side, and now this version of the equation, all the terms on the left-hand side have a dy over dx, so now is a good time to factor. So again, it's important not only to know how to do these steps, but if your algebra is weak, it's important to know the best order to do them in. Okay, and now we can continue to get the dy over dx by itself. You probably know how to do this next step. We need to get rid of this cosine x minus 4y cubed term. Well, it's being multiplied by the dy over dx, and the way you cancel out multiplication is with division. That accomplishes our goal of getting a single copy of dy over dx all by itself on the left side of the equation. And everything else is on the right side of the equation, which is the definition of a solved equation. And here's our answer. The problem was asking us to solve for dy over dx, and now we've done that. We've solved for dy over dx. Okay. By the way, again, you don't have to put in all of these parentheses that I've been putting in here necessarily. Some of these parentheses could be removed. I was just trying to put in maybe more parentheses that was necessary for extra clarity here. Okay, so here's our solution. This is the correct solution. Let's go back up and see the incorrect approach that occurred during the tutoring session. So again, one problem was the student had difficulty moving this term from the left to the right-hand side, as I suggested, they would probably have had less trouble if they changed this negative sign into a subtraction. So that was my primary algebra advice here. Also, I think it would have been better for the student first to move this term to the left and only then to move this term to the right, rather than trying to do those simultaneously. If your algebra is weak, it's better to only do one thing at a time. And finally, perhaps you noticed that we also accidentally just left out a term. We accidentally just dropped this 3x squared term. So there was really two mistakes in this line. One mistake is that the signs are wrong on this term, and another mistake is that we just accidentally left out the 3x term when we were recopying. And here again is the correct solution. And the main idea that we went over here is that when you have algebra that involves negative signs, it's oftentimes a good idea to turn the negative into a subtraction sign. That might make the algebra clearer to you. This is a letter B. Okay. So when I write a 6, I write it like this. And when I write a B, I try to put on this little cursive tail to distinguish between them.
B.
Let's try this.
Okay. AB plus C plus F plus G squared. And solve. All right. Well, oh, my mistake. Okay, we're solving for U. So I could do the same thing. Had E on both sides. So I guess I shouldn't have done this. Solve for E. Keep E on this side. Minus AB minus F. Factor E out. CD plus G squared. Divide by CD plus G squared. And we get this. Okay.
Okay, that was very good. That was excellent. You made a few mistakes on that problem, but that was okay because you caught all the mistakes. So you just took your time. You double checked each step. It's natural to make mistakes. The important thing is to take your time and catch them. So that was a good process. All right, so this is important algebra for us now. So let's review the key things. So one thing here is make sure you're solving for the right thing. Obviously, make sure you're solving for the right variable. At first, you were solving for the incorrect variable, but you double checked yourself and backed up. So that's good. So one thing that you had to do here is you had more than one e on the left-hand side, right? You had more than one e on the left-hand side, so you couldn't solve for e until you had only one e on the left-hand side. And what was the technique that you used to go from two e's to only one e? Well, you factored, right? But the important thing is notice you didn't factor in your first step. First, you moved all the terms that didn't have an e to the other side. So it's important not only to do the right things, but in the right order. Notice it wouldn't have made any sense, or it would have been less natural to factor the original equation. You can't really factor an e in the original equation, or not as simply, because some of the terms don't have e's on the left-hand side. So you did things in the best order. First, you moved all the terms that didn't have e's to the other side to get rid of them. So that was a good step. Only then did you do your factoring step to reduce from two e's to only one e. So you did the correct things and also in the correct order. Also, something that you saw was that at one point you thought you were solving for e by getting e by itself on the left, but you realized it wasn't working because there was still an e on the right-hand side. So it's good that you caught that as well. You can't solve for a variable unless you've got only one version of that variable in the whole equation. There can't be one on the left and one on the right. So it's good that you caught that and backed up as well. Okay, so that gave you some trouble, but it's good that you took your time and worked it out. You did come out to the right answer. That's good. I'll go back to my screen then.
Okay.
Let's try this.
Okay. AB minus CD.
And what we're going over now is we're trying to focus on the skills that you need based on that, especially on that sample exam that we looked at. So these are all necessary algebra skills for the test.
For sure. Solve for D. Okay. So we have D on both sides. So we can get AB minus CD minus DG is EF. And then oh. Okay. So if we factor out a D, I guess this doesn't matter. I'm just going to leave it like this. Okay.
Let's see. Okay, good. All right, good. So this is some algebra that's giving us trouble before, but we got this right. So again, what are we solving for here? D. Now this problem was slightly harder than the previous one because we started not only with two D's, but they were on different sides of the equation. So what do you do when there's two D's on different sides of the equations? Well, as you remember, the first thing you have to do is get them both on the same side. Notice that, again, it's important to do things in the right order. It's pointless to move the A, B around until you've gotten both D's on the same side. That's something that's messed us up in the past. So there's no point moving the A, B from the left to the right as long as the D's are on the left and the right. So it makes much more sense to do these things in the order that you said. First, you move both D's on the same side, and once you have both D's on the left-hand side, you can see that now you have to move the AB to the right-hand side. And again, it doesn't make sense to factor out the D's until you've moved the AB to the right-hand side, just like you did. So you did that well as well. It wouldn't make sense to factor out the D until you move the AB to the other side, or it would make less sense anyway. Okay, it looks like you were careful with the negative signs as well. So EF minus AB. Okay, it looks to me like we ended up with the correct answer there as well. Good, so that's some good progress on some important algebra for us. I'll go back to my screen.
Okay. XY, 3x squared minus y squared equals 3x.
Okay, let's try that.
Okay. Alright. So take the derivative of both sides, respectively. Okay. So Now we need to use probable. Okay, so we have dy over dx, that's what we're solving for. We have it on both sides. And it's coupled. So, and we can now move this over, so minus 2y plus 2y 6x. Now we can factor. So, negative 2y minus 2x equals 2y minus 6. Okay, so we add this expression, we add this function, and find the derivative of y with respect to x. So we took the derivative of both sides.
Okay, that's good that you're going back to check your work. That's a very important step. And it looked like you were checking your work as you went, so that's good too. We got a lot of material covered, so to save time for today, I'll just tell you that you got it right. It's when you're doing it on your own, it's always important to go back and double check. But we'll save time, and I'll just tell you that you did get that right. Good. Okay, so let's see. Let's scroll back up to the beginning then here. It's a big problem. It doesn't even appear on the screen. So you see, we covered a lot of material here. That shows some good progress. There was lots of calculus and derivatives here, and there was also a lot of algebra. And it looks like we executed all of those steps correctly. There was a couple of places where you made mistakes, but you caught them as you were going. The best time to catch a mistake is while you're doing the problem, not when you go back and check the whole thing later, and that's what you did. So that's good. That's a hard problem. So this was a problem from the sample test. Again, this is a pretty hard implicit differentiation problem, but that was on the test. So it's good that you were putting things together to get that right. Okay, so it looks like you would have gotten full credit on that. I'll go back to my screen though. Let me just show you maybe a slightly better notation for this. You did kind of skip a step at the beginning. At the beginning, I think it would have been safer to write this so that you really understand what you're doing. The way implicit differentiation starts is by taking the derivative of the left-hand side of the equation and setting that equal to the derivative of the right-hand side of the equation. And then you can use the sum and difference rules
Yeah, that makes a lot of sense because I was wondering what to do with the 9 for a second, and I guess if I wrote it that way, then I wouldn't have been wondering at all.
Yeah. So one reason I'm mentioning that is because I noticed that you had a fair amount of trouble with your first line. Now the good thing is that you just took your time and worked it out, but you might have had less trouble if you had written out more of the steps like this, like you were just saying. So I would have actually written the first 2 lines like this, and then it might have been clear what you were doing. You ended up doing it in your head, and you did it correctly, but it's safer to write down each of the steps. Now, as the class goes on, you're going to start doing more of these steps in your head. But since this is the chapter where we just learned this material, we want to be writing every step down on paper. Okay. Something else I noticed is that at the beginning of each equation, you wrote this, like so. That's actually a notational mistake because this makes it seem like this equation is equal to the previous equations. But equations can't be equal to each other. The left side of an equation can be equal to the right side, but it doesn't make sense to say that this whole equation is equal to the whole previous equation. What you might have been thinking about is sometimes people do something like this. They might say y equals 3x plus 4x, and then you could put this equal here. But notice, I'm not saying here that this is just a shorthand for saying that this right-hand side is equal to the left-hand side. It doesn't make sense. On the other hand, you wouldn't do this. So this is okay, and this is wrong, if we can see the difference between these. It's wrong to say that an equation is equal to another equation. It's okay to say that this right-hand side is equal to the left-hand side, and we just got lazy and didn't rewrite the left-hand side, or we took an acceptable shortcut and didn't rewrite the left-hand side there. Okay, so it's worth taking the time to get that notation as careful as we can. Also, I think I noticed, I think you wrote down this here. How would you read this term aloud?
This is the derivative of y squared with respect to x.
Excellent. So what are we taking the derivative of?
Of y squared.
That's right. But if we're taking the derivative of, so what does this d stand for?
D is derivative. Well, the top is the top D. Yeah, and then the bottom D is.
So what does the top d stand for?
Top D is derivative.
Derivative of.
Of.
So
y.
it would make more sense if you think about it to write it like this then. Because we're taking the derivative of y squared. The parentheses here tell us what we're taking the derivative of. Now, you did take the correct derivative, but this is a better notation for that step. Okay.
Okay.
Okay. All right. Good. So that's good progress on implicit differentiation. That's a pretty tough problem. Although this might not be the hardest they could give you. They could make this even harder by throwing in some trig functions. So that's something you should practice on your own. But that's still a pretty tough problem. So let me add on a part B to this. Same problem.
That's fine. Yay. Okay. Fine. Okay.
Okay. Let's try part B.
Okay. It is the same curve.
Now, we haven't quite done a problem just like this before, but we've done pieces of this. So we should be able, even though we haven't done something exactly like this, we should be able to put the various pieces together and attempt the problem. So give it a shot.
Okay. So, okay, so they give us both points. That's good. And we need to use slope and intercept. So we need the slope of this function, of this curve. Well, at the point. So, yeah. I usually like to use point slope, but I guess it's the same. All right. Is this okay?
Okay, well, that needs some work, so let's talk about that. All right, so let's see here. So you tried to go directly to the equation that they were asking you for there. So one problem with that is, do you know in the y equals mx plus b, what does the m stand for?
The m is slope.
That's right. Do you know what the b stands for?
The b is the y-intercept.
That's good. Do you know what a y-intercept is?
Yep, it's where it intersects the y-axis.
It's the y-coordinate when it intersects the y-axis.
Right.
Good. What would be the x-coordinate for the y-intercept?
The x-coordinate.
Yeah. What's the x-coordinate for the y-intercept?
Well, I know this is xy, but isn't x just... It's just a variable, isn't it?
So draw an xy axis. And now draw a curve that crosses the y-axis, any curve you like. Put a point for the y-intercept. Good. What's the x-coordinate of that point?
0.
Okay, good. So what is the x-coordinate of a y-intercept?
It's...
I just wanted to apply what we were just talking about. You've just shown the y-intercept on your graph, right?
Right.
What's its x-coordinate?
0.
Good. So what's the x-coordinate of any y-intercept?
Oh, it's always 0. Okay.
That's right. Otherwise, that couldn't be the point that crosses the y-axis.
Okay.
Okay. So in this problem, they gave us the point 2, 3. Is that point 2, 3, is that the y-intercept?
It is not.
Because what would the x-coordinate have to be for it to be the y-intercept?
0.
So they gave you a point on the line, but they didn't give you the y-intercept. They gave you... so we can't plug directly into y equals mx plus b because we don't know the y-intercept here. We don't know the y-intercept for this problem. Okay, so instead...
I guess...
Yeah, you were saying?
So could I plug both of these into our derivative, and then that will give us slope?
That would be a good idea, yeah.
Okay.
Okay. That's a little unrelated to what I was just talking about, but that's something we need to do as well. We can't just phrase the slope with a y and an x in it. The slope is supposed to be... Is the slope a variable or a constant?
Slope is a constant.
Right, so we need to get a constant for the slope. So that is something else we need to do on this problem. So let's try that.
Six minus 12. -6.
I think you might have, go back and where are you getting the formula for the slope? I think you miscopied that.
2y minus 6x over negative 2y. Oh, I did. So negative 2 times 3. Okay, so negative 6 over negative 6 minus 4. Aha. Yeah. I kind of wanted. Well, no, that would have been wrong. Never mind. Okay. Anyways.
Let's check our arithmetic there.
2 times 3, 6 minus 6 times 2 is 12, negative 6. Over negative 2 times 3, negative 6 minus 4. 2 times 2 is 4. So negative 6 minus 4 is negative 10.
Okay, now we have the slope. Okay, so now we need to write the equation of the line. So what would be the most convenient form to start by writing the equation of the line? We have the y equals mx plus b, but we also know point slope form. Well, which way would be the most convenient way to start?
Point slope.
Because do we know one of the points on the line?
Mm-hmm.
And do we know the slope?
Yep.
Yeah. Why is it not convenient to use y equals mx plus b? Well, what does the b stand for?
The y-intercept.
And do we know the y-intercept?
We don't.
No. So even though the question's asking us for y equals mx plus b, that's not the convenient place to start. Okay, good.
Y minus 3 equals 3/5 x minus 2. Okay. So now we have that. We have the slope. So we find the equation of the tangent line. Well,
Okay. So now, what does that equation represent? That's the equation of the tangent line at the point 2, 3. The only problem is it in the form that the question was asking us for?
no,
No, it's
sorry.
not. So we need to now use algebra to rearrange the equation so it looks like y equals mx plus b.
Okay.
So now we use algebra to rearrange it so that it looks like the y equals mx plus b form, since that's what the instructor is asking us for.
3/5 times 2 equals 6/10. So 2, 3. Well, 3/5 x. 3/5 times 2. Well, I need a remedial math class. Okay.
Yep, unfortunately, most people have forgotten how to do arithmetic without a calculator. But you're allowed to use the calculator on the test, right? So.
Mm-hmm. Okay, this makes good sense. Slope, intercept. Let's double check. 3/5 x minus some junk y equals 3/5 x. Okay.
Okay. Good. So what's m?
Slope is 3/5.
Good. And what's b?
B is y-intercept, and the y-intercept here is 1.8.
So notice that we've now discovered something that you wouldn't otherwise have known. What is the y-intercept of this curve?
It's 1.8, so
Good. So what would be the x-coordinate for that?
the x-coordinate for that is
For the y-intercept.
0 for
Yeah.
0.
So we know that y-intercept would be 0, 1.8. So you can see that there's no way we could have plugged in 3 for b, because that was not the y-intercept. That was just another point on the line. Okay. So, all right, we haven't done a problem quite like this before, but this does build on some of our previous skills here. So you can see that when there's a problem about implicit differentiation, your instructor likes to follow that up with a kind of tangent line question. This is another problem from the sample test, so it's good for us to be working on this. Okay, so notice here, even if they tell you to use y equals mx plus b, that doesn't mean that it's most convenient to start with y equals mx plus b. It was still most convenient here to start with the point slope form of the line, and then we had to use algebra to rearrange it so it looked like y equals mx plus b. Also, at first here, I think that you were just plugging in 2y minus 6x over negative 2y minus 2x for the slope, but we actually have to get a number for the slope here. Let's, for your notes, let's erase the first equation you wrote down here, since that turned out to be a mistake. The y equals 2y, yeah. That turned out to be a mistake. Okay. Now remember that when we did tangent lines before, we always then tried to draw a graph to show this graphically, but we can't do that here. Because remember what we were doing before was graphing the function, graphing the curve, and then showing the tangent line. And how did we draw the curve? Well, remember we were using our calculator to draw the curve. But this curve, our calculator can't do. Because go back to the original start of the problem.
It's because it's a funky
Because it's not solved for y.
Oh, I'm sorry.
It's funky in the sense that the original equation was not solved for y. And it would be difficult to solve it for y. So our calculator doesn't know how to graph something that's not solved for y. So we won't be able to really draw a graphical interpretation here, but hopefully we have a kind of feel for what it is, since we drew the graphical interpretations for tangent lines earlier. Mm-hmm. Okay, I'll go back to my screen then. So one thing I wanted to show you then. So on your calculator, if you were going to try to graph this, notice that when you're graphing, you have to type in the equation here, right? But the calculator says, first solve for y, right? The calculator's assuming that you've already solved for y, and then you write y equals here. So the calculator wouldn't know how to deal with something like this, which is not solved for y. So that's why we can't graph this on our calculator, at least not easily. All right. Now on this problem, you had ended up with dy dx equals, let's see, what did you have? 2y minus 6x over negative 2y minus 2x. Okay, and then when you were using the point slope form, you were using this. Now, how can you, let me show you the best note. So you wrote down that the slope here then was 2y minus 6x over negative 2y minus 2x. Another way you could have written that here is that the slope then is y prime of what?
Y prime of the derivative of...
So what we want to do is put the input here. What's the x-coordinate where we're trying to find the derivative?
2.
Yes. So you might have started with this. Although notice that on this problem we were using this notation, right? For derivative. Now notice one problem with this notation is it doesn't have a slot to put the input number. So let me show you what the notation is for that. It's not as it's not as clean as before. But when you're actually plugging a number into the derivative, here's the notation when you're using the dy over dx notation. This is a notation we haven't had to use before. So my point here is that dy dx bar x equals 2 is the same as, these are two different notations for the same thing. So it's always good to have a good notation here. And this is what, and then we plug that. So this means plug x equals 2 into this formula. And of course, actually, maybe here we also had to plug y equals
Okay, I was going to ask
3.
that. Cool.
So you could also write it like that. In fact, in this case, that would probably be the best notation to use. So here's how we write the derivative when it's got variables in it. But when we're plugging in numbers, we use the bar to show what numbers we're plugging in. All right, one moment. All right, so here's part C for the same problem.
Okay. Okay. All right. So our original equation was, well, first we define the slope. Two y minus 6x over negative 2y minus 2x. xy. Okay. Minus 6. Negative. Okay. So far we have slope x1, x1, y1. So minus so minus 0.111 plus 0.6. So this is slope intercept form. And 2.49 is b, which is our y-intercept. So when x is 0, y is 2.49. And yep, I think we're good.
Okay, so what's the answer to the question?
Equation of the tangent line to the function is y equals 0.111x plus 2.49.
Okay, excellent. That's right. That's the answer. Okay, so that was just a little extra practice on this approach of the tangent line. Notice that if you move to a different point on the curve, the equation of the tangent line is different. We had to do this all over again. Did this tangent line have the same slope as in part B?
I did not.
And did it have the same y-intercept?
Nope.
No, it's a whole new line. Remember that we did some graphical problems in an earlier session where we drew multiple tangent lines to a curve, and we saw they each look different and have different equations. So that shouldn't surprise us here. So that was a good use of notation. You used the dy over dx with the bar notation. I think that was good. It was also good how you summarized your information, your m, your x1, and the y1. That was a good systematic step. Okay, so I'll go to my screen. Now remember, we can't really graph this function easily because the equation is not solved for y, so it's hard to put it into our calculator. But we do, let's see. Remember that part B was asking about this point, 2, 3.
Mm-hmm.
So we know this point is on the curve. And what's the other point that we know is on the original curve?
0 plus the y-intercept. So
well, actually, no. That's on the tangent line. That's
okay.
not on the curve. The other point we know on the curve was given in part C, 1 and 2.6. So we know these 2 points, and we know a little bit about the tangent lines here. For example, let's see. Here's the 2, 3 point. So was the slope here? What was the slope at this point?
The slope at 2, 3 was. Back up. 3/5.
Yeah, that's right. So what does that tell us? Is the curve upward or downward sloping
okay.
here?
The curve is upward sloping.
So we know the curve kind of looks something like this at this point, although quite shallow. Shallow at this point. So the curve kind of looks like this. And then how about at this point, 1, 2.6, what's the slope there?
The slope was 0.111, so it's also upward sloping.
Good, but steeper or shallower than at 2, 3.
It would be shallower.
So we can kind of see here that we have a shallow slope here and a slightly higher slope here. So the point is that we can use the derivatives to start guessing what the curve looks like. Very shallow at both points, but increasing slope. So I just wanted to show you this is kind of the use. Even though we could actually, if we found the derivative of enough points, we could guess what the curve looked like. by drawing short segments of it at every point. So I just want to kind of show what the practical, what kind of a practical application of this is. These videos are offered on a pay what you like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.